Good morning, everyone. Welcome to the 1 week online faculty development program on the mechanics of composite materials and structures, sponsored by AICTE Training and Learning Adult Academy, that is going to held at Department of Mechanical Engineering, Engineering College, JNAT West University, Jodhpur. About MGM Engineering College is one of the oldest government engineering colleges in India. The college was established on 15th August 1951 by the government of Rajasthan. Later in 1962, the college became a faculty of JNAD University, Jodhpur. Our alumni are holding prestigious positions in various industries across the globe and government offices. Many of our students are working as professors in IITs and IIMs and other prestigious technical institutions. Currently, the college is offering 11 BE courses along with BR, MCA, ME, and PhD programs in various engineering disciplines. The vision of the institution and the about MBM college. The vision of the institution is to be leading educational institute that provides quality technical education and conduct research to produce knowledge-rich professionals for meeting the dynamic needs of the industry and the society. Mission of the institute is to impart quality technical education to the students to make them globally competent engineers contributing to the development of the nation and world at large. About the composite materials, laminated composite materials are used extensively in aerospace, defense, marine, automobile, civil, and off structures. Large parts of wind turbine blades and many other industrial applications where low weight is a critical design parameter. Composite materials have extraordinary properties like high strength, high stiffness to weight ratio, good fatigue durability, resistance to corrosion, and the damping properties. So, in this faculty development program, you will learn in the detail about the mechanics of composite materials and structures. Our chief patrons are Professor P.C. Trivedi, he is the Vice Chancellor of the Jain and Vyas University, Jodhpur, and the Professor S.K. Oza. He is the Dean of the Faculty of Engineering and Architecture at Jain and Vyas University. Our patent member is Professor Dinesh Shringi. He is the head of the department in the Department of Mechanical Engineering. This is our advisory committee, Professor Rajat Bhagwat, Professor P.M. Meena and Professor S.K. Singh. Our dedicated Mechanism of Composite Materials team. This is the schedule for the day 1. The first session will be held by the Professor S.P. Harsha. He is working as a professor at IIT Roorkee. It is our pleasure. He is also our alumni. He has earned his bachelor degree and the master degree from the Mcms Engineering College, Jodhpur. The second session will be taken by the Professor S. Pradyumna. He is the Associate Professor at IIT Delhi. And the third session will be carried out by the Professor Chandrasekhar Yaramili. He is Associate Professor at IIT Bombay. This is the schedule for the day 2. This is schedule for the day 3. And this will be the schedule for the day 4. This is the schedule for the day 5. On the day 5, we will also having one session by the stress management and holistic development session through Sahajan Yoga by the Sri Nishal Kapoor. These are our eminent speakers, and the rules and regulations for this faculty development program. A test shall be conducted through Google Form. The certificate shall be issued to those participants who have attended the program with minimum 80% attendance and scored minimum 60% marks in the test. The thanking you. Now I like to invite our moderator. Please invite our expert, Professor S.P. Harsha.
Thank you, ma'am. Learning gives creativity. Creativity leads to thinking. Thinking provides knowledge, and knowledge makes us great. Truly said by Dr. APJ Abdul Kalam, which signifies that knowledge with action converts adversity into prosperity. But knowledge without action is useless and irrelevant. So don't crawl, fly, and fly. I, Urjaswata Pridarshini Gaur, the moderator of this program, warmly welcome all the eminent speakers and participants on this first day, that is 9th of September 2020, on the 1 week online faculty development program on mechanics of composite materials and structures, sponsored by AICTE Training and Learning Academy and hosted by MBM Engineering College, Jodhpur. I express a heartfelt gratitude to all. Now, I take the pleasure of inviting our first eminent speaker of the morning, Professor S.P. Harsha. Professor Harsha is one of the jewels from our college who have received B.Tech degree in mechanical engineering and M.Tech degree in thermal engineering from here itself. He did his PhD in nonlinear dynamics and control from BITS Pilani and received his postdoctorate in 2007 under the US Defense Project Dynamics and Control Lab, Philadelphia, USA. He has a teaching experience of over 20 years, imparting quality education in eminent institutions like the Villanova University, Philadelphia, USA, IIT Roorkee, and BITS Pilani. He has 150 publications in international journals and is the author of 7 book chapters in books renowned worldwide. He has many feathers in his caps, some of which include an unmatched experience in national level projects like the projects with ISRO, 2 in THDC Tehri, 2 projects in DST, 8 projects in BHAL, and 5 projects with Indian Railways. Sir, we are blessed to have you in our portals. I invite you, the beacon of knowledge, to take us all on the journey to the land of composite materials and dynamic analysis of sandwich functionally graded material plates. Kindly take over, sir.
Good morning. Good morning, Professor Bhaskar. Thank you. Thank you. Yes, so nice of you, and thanks for the invitation. I hope now I'm visible and audible too. Wonderful. I thought maybe I'm just late. Will it be okay? Actually, I'm not that late. Oh, excellent, excellent. Because I was just checking the email, and then I found it that the inauguration is there right now. And okay. So at what time we are planning to start? And- Okay, okay. So let me first share my screen also for PPT. Uh, I'm sharing the screen. Here is the screen sharing. Where? Okay, present now. Okay, okay, okay. So I click it and then your entire screen. Okay, okay, that's wonderful. So let me. Where's the presentation? No, where is that one? Is that so? Actually, we people are using mainly, this is not a common thing. We are using this WebEx and this Google. So this one, this Google Meet is pretty new. Let me see. Uh, screen presentation. This is where this presentation and how do I share window? No. This is where. Is it visible now? My presentation. Okay, wonderful. That's great. So should I start or should I wait for what? Okay, wonderful. So good morning, everyone, and thanks for inviting me for this talk. And I'm hopeful that probably I'm visible and audible too. So the okay, thank you. And uh, the topic of this talk is the dynamic analysis of sandwich functionally graded material plate. Actually, this work which I started way back, almost a decade back, on functionally graded material plate. Then we observed over the time that the sandwich plates are pretty popular, and this functionally graded material, since the theme of the this program is mainly on this composite material, so I thought of maybe I should focus on this aspect of my research. Few of the students of my research students, they worked on this particular problem, so I'm thankful to them that they contributed not only in developing of these plates, but also you see here mathematically we have done some kind of work. Today I'm going to present that specific part of the dynamic analysis, and then I'll start with basics, and then I'll go to the response analysis. So if we are going to the basis of that, then the plates are there. Plates are a very important component, especially when people are talking about any structural component. Without plate, we cannot even imagine. So like if we are saying about the boiler, or if we are talking about the turbo machinery, outer shell, or even if we are talking about any mechanical component, plate or shell are the basic elements you see here. So we need to analyze that. Over the time, we observed that the conventional materials are not sufficient because they are not giving the appropriate property, the desired property which we are looking. So generally, we are going with the plates and shells. So the today's talk is mainly based on the plates constituted of the functionally graded part. So plates are nothing but the structural element which have you see here, like where various applications are there. And if you are talking about the plate, we generally observe that there are basically thin plate. And in the thin plate now, if they are, you see, having very small elastic deformation, very minimal elastic deformation, then we are simply saying that whether it's a deformable plate, the flexible plate, or stiff plate. But if we are going for the larger deformation, means the larger deflection, like in a space, we have done, you see, some kind of space structure, the membrane structures, you see here, in which the antennas and lots of you see things in which the inflatable features are there, then we need to analyze with this kind of, in which the large deformation, large deflection problems are there. And there we have different kind of relations, the constitutive relations between the different, this we can say displacement, strain, and corresponding stress component. So you see here, just merely having a different aspect ratio, the thickness to width ratio, if you are just changing, the entire phenomena, entire physics is different. Even they are coming in the same domain of thin plate. If you are going for our mechanical purpose mainly, the structural purpose, we have various thick plate considerations are there, in which moderately thick plate, where you see the dimension of thickness to width is more than 1/100 or 1 by, like beyond that, or the thick plate. Why we are configuring these things? Because we all know that under the load application, whatever the strain components are occurring, whether it is the in plane strain, out plane strain, under, you see, we can say, like the banding or the shear, or towards, you see, the axial component towards the transverse direction, whatever the stress distributions and the corresponding strain distributions are there, they are absolutely sensitive to what kind of domain or the plate is, whether we are analyzing in the thin plane domain with a small or with large deflection, or whether we people are just going with a thick plate feature. So that's why this configuration, the first to choose that configuration is very important. And when we are going to that, we need to first define the constitutive relations, that what exactly our main domain is. So if you look at the screen, you'll find that these are basically this displacement or reflection distribution is. So initially, when we are saying it is undeformed, certainly you see here, we can keep that, okay, since it is a well-aligned, features are there along the lattice structure, along the axis, along the neutral features, you see here, they are all well settled. Because there is no, as such, the localized deformations are being happening. So since it is not there, so we don't have any deflection criteria together along the plane. So this is first condition. If you look at then we have this part. Then we are, let me put this pointer here so that it will be easier for me. Okay, so here this is the undeformed condition. But when we are going to the deformation theory, then there are basically the basic theories are there. I'm not going into detail because I need to go into the other part. So generally we are classifying according to what our constraint conditions are, what our main aim is. If you are just saying that, okay, now the classical plate theory or the Kirchhoff theory, or this is the basic theory which was almost devised in way back in the 1890s, so that theory is there, then we can say that, okay, there are, you see, the constraint conditions are there, that our main theme is to just say that, okay, the plane remains same before and after the deformation. And then you see whatever the deformation which are happening, you see here, they are absolutely aligned to that. So you see here, even when we are going toward the transverse direction, or whether we are going towards this direction, you see here, the deformation remains same. And then even you see here, the transverse strain is absolutely remain constant, or you see here, it is almost assumed to be absent. So when we are going for a simplicity of the deformation, and you see the stress components, if you look at that, this is a very small deformation is being assumed along that. So this deformation is assumed here where that you see these things are happening in both the direction. You see here in this part and that part remains same. Then we can say this is the the simplest theory. And if you look at the distribution of this, that what the displacement distribution is there or the deflection happens. So this is the initial and then this variation. This variation has two main components, that towards you see the transverse direction, how you see the deflection happens. So what is the gradient feature? And then this gradient feature is being driven by the two main part. One, the function, and this is you see this important part, the shape function. That how you see you are considering the variation along you see the thickness direction. So if I'm talking about this particular direction, the vertical direction means we can say you see the thickness direction, then what exactly the property variations are being considered. Again, remember, you see here, this f of z is simply giving you the geometrical feature along with the material distribution. And that's why you see the functionally graded material having some kind of attentions. So either we are going with the three-dimensional feature, so we have U, V, and W, you see, and then this is the variation. So when we are going for the classical one, then we are simply going with the 2D variation, and then we are assuming that the third variation is almost remain absent. Then we are going for the first order shear deformation theory. The first order shear deformation theory is also known as the Mendelian rational theory. It's a very common theory, very popular, because here they are absolutely giving you the correct displacement deformation, the displacement feature. So here I'm using two words. One, the deformation. Second, the displacement. These displacement features are very important because they are absolutely giving you the discrete phenomena of deformation. So when it is being deflected, you see here, and displacement happens in both x, y, z direction, or u, v, w, I would say. Then you see here, we are simply saying that since we are going for more accurate the displacement part, so you look at that. The in previous theory to this theory, you see here, now we are going with more accuracy part. The stresses are not, more accurate when we are going to the first order shear deformation theory, because here the shear deformation is assumed to be linear. And you know that the stress is basically a tensor domain. But since under you see the elastic feature, using Young's modulus feature, you see here, we are saying that we are not going for the shear deformation, whatever the shear variation is there of higher order. We can go for higher accuracy for the TSDS. So TSDT or FSDT generally. So third order or higher order shear deformation theory, in which you look at that. Even these things are happening, like the deflections are happening, but the distribution wave from you see top of the neutral axis and bottom of the neutral axis is not linear. Here we are assuming all the linear feature with that part, but here we are assuming that how you are distributing, how the material properties are absolutely varying along you see the the thickness direction. We are using the shape function, so lots of shape functions are there. So these are basically the shape function f of z, as I told you. See in this is one of the typical factor here in this. So we have, you see, right from 1960s to here until date, even the shape functions are being derived. And they are why they are deriving, because we are just interested to see that how precisely we can evaluate the displacement and the stress together in plane or out plane. So that's why you see here, like these classical plate theory to higher order the shear deformation theories are well applicable. According to the domain, according to the load application, we are evaluating, or we are trying to see the compatibility of both the things together. So this is, you see, the deformation, and this is what one of the basis part of plate theory is. So when we are going to our now, so this was the geometrical part of that we have a plate, and you see the plate theory, so thin plate, thick plate, even small deformation, large deformation, and then you see here the various kind of the shape functions which are being there to describe the property variation along you see the cross section. But what property? So we need to first go to define that whether we are going for the material aspect. So what kind of you see the metal aspect can be chosen, or what is the basis of choosing that? So the first is alloys. You might have, like the alloys are pretty common in right from our undergraduate level. We have studied a lot. You see here, like the steel is there, in which the iron and carbon is there. So both at the material level, the microstructure level, you see these alloys are being constituted. or even brass or bronze or all these components where you see the metallic components are being essentially present. We are simply saying that you see here, like the alloys are a mixing of two or more metal and non-metal at the molten state. So at the microstructure state, you see here, these things are there. So generally we have discussed and we have already, not we have discussed, we have already studied those things. This is the basis of that. But then you see, we observed that they are pretty bulky. In many applications, they are not at all essential. Like you see the ambassador car. And now these cars, what is the change? The changes are there from the material aspect. There is no as such you see change in the engine design from the we can say the geometrical aspect, but from the material aspect, a lot of changes are there. So first the alloys, the basis, then we are going to the composite. The composites, when we know that okay, now you see here, since every time we don't have to go to the melting temperature and then make the constitutive feature and then prepare the alloys, we can even go to the macrostructure feature and we can simply constitute the things. So the advanced materials which we are saying the composites having you see one or more materials in the solid state. So here we have a matrix, and then you see here we are reinforcing something. So in the reinforcement, or even you see here when we have laminated feature, we need to check it out that what exactly the compatibility and what is our demand is. Like you see, we are saying metal matrix composite. So the matrix is metal, and then you see here we are reinforcing something. What exactly the property? Whether we are going for higher toughness, whether we are going for higher, like the hardness, higher stiffness, or what exactly the cutting tool properties are there? What kind of properties which we want to enhance? Accordingly, we can reinforce that. So the composites are, even if you look at the composite, they are also of now of a very limiting state, because now we have the smart structures, the smart materials. The material itself is smart. So you see, as far as the composites are concerned, they are basically of passive nature. They don't have any active nature. So sometimes we feel that okay, biodegradable composites are there. We are adding main things, and according to our requirement, the desired properties are to be achieved. But now the things come up from this. So this is what you see, like the composite, the fibers plus matrix, and then you see here, at various stages that can be, like form the composite. The functionally graded material. It is of the, we can say, the recent decade, you see, since we are going in the industry 4.0, these materials have lots of applications. I'm giving you an example. Like you see, like previously, if you might have experienced the thermal power plant. Previously, when 35 years or 40 years back, when we installed various thermal power plant, then you see the single units are of 100 megawatt, 200 megawatt. These units were there. Coal, the water, we haven't changed that one because we can't change those things. But now a single power plant is of 800 megawatt, 800 megawatt supercritical features. How this has happened when the input part is not changed? We cannot change, you see, the property of water. We cannot change the property of coal as well. But now we have the internal processing unit that can be even go up to that part. So now 660 megawatt to 800 megawatt, each unit is now able to produce that much power. So this is because of the material enhancement. So that's why you see here, this is the era, and the forthcoming for the industry 4.0 is where the automation is there. It's purely on these kind of smart structures. So functionally graded material is also one category of smart structure material where the properties at two extreme ends of the material, maybe at any we can say thick, thin, whatever it is you see here, they are absolutely different. Just like our teeth, the human has, you see here, like lots of these functionally graded materials. The human teeth, if you look at on the top of the teeth, it is having all shearing phenomena. It can crush the things. It can simply bend the things. But if on the other side, the root of the teeth, if they are functioning like that, and even if you look at that, they have a conical structure. If they have the similar kind of function, then certainly you see here our jaw is almost gone. But they have the suspension and they have the damping property. How this has happened? On top of that, there is a cutting property. On below, we have a damping property. This is the beauty of the human nature is. And that's where you see the functionally graded material comes. At one side and on other side of the material, they have almost opposite properties. So the properties are varying with the change of dimension is functionally graded. The functionally, like according to the function, they are being graded like that. So here it is. We have different phases of material. and their concentrations are looked at that point. So we have, you see here, the extremely at extreme end, we have one concentration, and on the other side, you see here, they are almost absent, remain absent there. And in between, you see the transition features are there. So, like with these continuously changing property, we can see that whatever the mechanical property which is being achieved according to the material concentration, material configuration, they can be arranged itself, they can be reproduced itself. So this is there, you see here, there are lots of, like we can say the smart structures are there, the safe memory alloys are there, piezo based are there, lots of magnetorheological, electroheological, lots of smart materials are coming, but this is one kind. Then when we are going to this, that okay, now the property variation is there, how this is there. So now we are trying to see that how physical phenomena can be mapped into mathematical way, because that's what the engineers are doing. Engineers cannot every time go to like the realistic part and then fabricate everything. First they need to see the compatibility, they need to see that what is the feasibility with the accuracy, that this should be accurate, and then you see here we need to check it out that what exactly the sensitivity features are there of all that part. So when we are saying that now functionally grading, so the grading feature is there. So what is the gradation laws? So there are mainly, again, this is a mathematical mapping. There are mainly three laws are there. Lots of updations are going on. Again, I would say lots of updations are going on every day, and you will find lots of papers there. So the first, which is very common, is exponential. That property, because you see here, say towards thickness variation, it is varying. We can say thumb rule that okay, now this is exponential, because this is very common in our that parabolic distributions are there of y square equals to 4x or x square equals to 4ay. So this variation is there. And here, since we people are talking about the this transverse variation, so the thickness is there. So z by h, this is one of the important. So here we are saying it is varying, and this is varying e to the power p, where you see here, like we can change the p, and then accordingly you see here that this is the index, that how much, what exactly the indexes are there. The power law, another, that sometimes you see here, it is not always you see here varying in a linear, or some you see in the constraint feature. We can go to the power index of this. So now this is, you see, this is, it is, the index is coming as a power from the exponential. So we can say now this is the power. It's not exponentially varying. It may vary with a square, with cubic feature, or with, you see here, like 1/2 or anything, according to the p, 0, 1 to any part you see here. According to the compatibility or according to the accuracy, we can simply choose the p. And that's why you see, since it provides us the flexibility of the distribution or the material variation, we are choosing this one. So this is still existing, and it has some kind of, like the attention because of the application. But important part here is there is the sigmoid one. Because nowadays, you see here, since we can go to the higher computational facilities, the sigmoid law is quite popular. So in the sigmoid law, now since we know that even in the plate or the beam, we assumed even that you see here we have a neutral axis. So from neutral axis to upstate, and from neutral axis to downstate, what exactly the variation? And there, this variation can be assumed in a nonlinear variation. So here, this is being inspired by the power law, but you see here, they have like say the z from, so the bottom part from 0 to minus h by 2. So even we divided the thickness into two configuration from the mid plane. That bottom part, the variation is this, where you see z plus h by 2, and the up part is h by 2 minus z. So this is what you see, the property variation, material property variation configured with the compatible mathematical description. So the geometry is simply defining that how the properties are being varying. So these three laws are there. So how they are actually working, this is what here. So we have, you see here, the power point one, you see. So even say we have like right now, you see the aluminium and alumina Al2O3. So the one side you see here, we have metallic, and other side we have ceramic. You see, both are different. One side, purely metals. We have all ductility features. And other side, it's purely a ceramic. And you see now it is absolutely integrated, and we have altogether the properties. So say, you see, if we are just going with 0.1 P, and then we are simply see that how the variations are happening. So this is what the one kind of variation where the Young's modulus and the Z are being integrated together. That how you see the elastic properties are varying when they are simply moving from one side, if you look at from this side to that side. This is what the variation. So you see here, we can go to this, but important part is coming as the sigmoid one. So this is my neutral axis, the zero. From you see here upstate, and then see h by 2 plus, and this h by 2 minus, and this is my z. So the previously which we defined the function according to the power, again I'm going back, according to this power, which is a driven part, we can choose that which one is more compatible. So this is what you see, the variations are there of the material property. Along with that, this distribution is showing both linear, because if the p is 0, you see this is what the straight one. But when you are simply defining zero point 0.1 and when you are going to the 10, the entire domain is being clearly defined, that how the distributions are happening across the cross section. And that's where the beauty of this, the sigmoid law is quite prominent. So in this, you see here, whether we can go, like both side, generally functionally graded material, we are defining piece FGM or SFGM, the power law driven or sigmoid law driven FGM, functionally graded material. So this is what you see the first part. Then lots of applications are there of these FGM, right? From nuclear projects to anything, communication. Now fibers are there. You see here, you'll find that even the lenses are there, energy sector, lots of, like, or the space part, as I told you, the memory structure. Now, since we just want to reduce the weight and we want to, integrate some properties which can even absorb the radiation under, you see, the cryogenic temperature, the functionally graded materials have lots of things. And then obviously, since these FGMs are coming from the human body, the artificial bones, skin, or any kind of dentistry feature, they are being devised from the functionally graded material. The different combinations are being there. Or even you see here, like the nuclear power plants are coming. So the outer shell of these things now. So now you see here, they are being upgraded using this functionally graded material, in which the inside temperature and outside temperatures are different. So how the thermal gradients are to be maintained. And then you see here, it has to have some kind of compatibility with that variation. That outside we have different temperature, inside we have different temperature. We need to see that, you see, how it can be acted as the isolator, thermal isolator, along with, you see here, whatever the internal operations are being there. So that's why you see lots of, like the applications which are going on. Now we are there is the sandwich functionally graded material. So this is another advancement, the sandwich plate. So in that, you see here, if you look at, we have two material configuration. Say, as I told you, the ceramic is there one side. We have on one side, you see here, the metal. But in between now, the sandwich part. Since you see, they are not just like the laminated plate, they are continuously graded plate where the properties are varying. So there is no, as such, the microstructural separation is there. There is no segmental features are there. They are up at the macrostructure features are not there. The microstructures are there, sorry. So we need to go with that. So again, you see here, we need to go with 3-layer, and in these 3-layer, we need to check the property variation of that. So that's why you see here, this is a very conventional feature and very important part, like in aerodynamic part, where you see the outside variation, the drag forces are coming, the temperature variations are there, and inside the comfort condition, they are very important because they are not only acting against the, we can say, the tougher feature, but also they are acting as a damper there itself. So there are lots of things you see here which are being going on, and we now we are going to analyze that. So when we are going, now the another domain is the dynamics. When we people are saying dynamics, that means you see here we are trying to evaluate the property variation in the domain of time. Now you see here in this, the realistic phenomena in the dynamics are the nonlinear systems. But generally we are, like going with the linear systems because it is pretty easy and it suits us. But that is not the accurate one. That is not the precise one. Because if you want to go to the robust analysis of any system, we all know that they are falling in the nonlinear systems. So as far as the linear system is concerned, they are pretty idle. And we can say that the known input, deterministic, or we can say the periodic, is simply giving the known, or without any ambiguity, the deterministic and periodic one. It's a very simple thing. But as far as the nonlinear systems are concerned, the nonlinear means it's not following the straight line. Maybe you see here, if I say that we have we can say the circular one, the parabolic one, the elliptical one. That means you see here, with the same one input, we may have more than one output. So which output is basically good, or which one is now suitable to our requirement? Then we need to go to the nonlinear analysis. So if you go to the nonlinear analysis, then the input is almost, you see, because it is in our control. But to this nonlinearity which is coming to the system, we have now, you see, the output part. So the output may be periodic, means you see whatever you see the things, if you look at the top, this is what you see here, the main phenomena. It may comes like that, but it is quasi-periodic, means now it is losing its periodicity. It is going to the quasi-periodic feature. Maybe see, like the things are pretty, means whatever we are saying that this is what my equilibrium point. It may hit, it may not hit, not hit at that point. We may have subharmonic feature. You see, with a single wave, now the wave is divided into two. So now we have two outputs, two unknown outputs, I would say, we can say two eigenvalues, or even more than that. Now, the chaotic one, the irregular pattern, it can happen to anything. So you see here, this is very important to find out the nonlinear analysis. So the nonlinearity, why this is there? Since the material itself, if you look at the functionally graded material, one side is metallic, so entire combination of BCC, FCC, and CP type of things are there. Other side is almost ceramic. They have a very brittle features there itself. So when you're combining together, certainly you see here, without putting the nonlinear system in the functionally graded sandwich plate, we cannot do anything. We even assume that whatever the displacement and the stress distribution occurring under the law, under the load, is linearly behaving, but that is not the accurate one because the material is not allowing. We cannot say that it is a homogeneous, it is a heterogeneous feature. Another part is the geometry. According to the, if I apply the load to metal and if I apply the load to ceramic, the deformation cannot be same. So we cannot say that when we apply the load, like we are assuming in the beam, like in solid mechanics, you apply the load intensity at one point, the point load is there. We are assuming that the uniform distribution is there across the cross section, and you see the dimension of beam is uniform. But we all know that this is inaccurate. We cannot maintain geometric linearity across the cross section. It has to have, where we apply the load, the bending is happening. The bending is of some layer. It is not the straight line. It has some, like we can say parabolic nature, maybe some kind of square, maybe some kind of hyperbolic if the load, the last deformation features are there. Then the kinematic. What is the constraint condition? What are the boundary conditions? Holonomic constraints, non-holonomic constraints. So you see here, the nonlinearity cannot be ignored. It has to have its presence in every realistic system. Like even in our teeth, even we are saying, you see, if you look at the geometry, they have different geometry and they have different functions altogether. Even they are functionally graded material feature. So even the material is same, their configurations are different, so their behavior is almost different. So this is what the behavior of nonlinear systems. This is what it is. Now the periodic, if you look at, this is the plate, the constraint conditions are there, and then you see here across the thickness, the variation is going on, deflection is there. If you look at the periodic one, they are well behaved. You can say that this system is exciting regularly in a simple way. So I have, you see here, the three excitation pattern, means the three excitation frequencies are there, the three loops are there. Like if you look at the three loops, pretty periodic, we can define the excitation pattern. We can define, this is the, like we can say the phase trajectory where the deflection and the velocity, means we can say the parameter and its derivative is there, and this is the actual phenomena, the quasi periodicity. Now if you look at the change from here to here, now even these distribution, the peaks distribution is almost different here. So sometimes you see now they are divided. So it is losing its periodicity. And but though you see here the outer periphery, the locus is same. It is not going beyond that. It is not simply showing any kind of randomness. Okay, but they are, you see here, they are having distributed within that. So if you look at each and every displacement of these nodes, you'll find that it is absolutely different than that. And then the chaotic one. Now this is what you see, the irregular pattern, where the fractal features are being happening. So we have, you see here altogether that, and you see this is the kind of excitation. So altogether, when we are simply putting the constraint condition and when you are going to the domain, you'll find that the excitation pattern is almost different. And this is what the realistic phenomena. So we need to check it out that when we are analyzing these plates or anything, any structure, any component, the signals are saying many things. How we are considering, that is all up to us. That is our analysis part. So the mathematical modeling, which is very important, we need to first go to that the selection of plate theory. Which plate theory is confined, and then how it is compatible to our main part. Once you define that, no, my part is FSDT is good one, because our main intention is to see accurately what is the deflection pattern is. We can go with that. We can go with higher order, the third order, and higher order shear deformation theory. First of all, we need to set up that. Second, the relation between the stress and strain, the constitutive relations. And then also important part is strain and displacement. This is the most important part here. We need to fix the relations there itself, because they are basically providing the realistic phenomena which is happening under the load, and how actually our domain is behaving. Once you fix that, then now we need to fix that whether we are going with the linear strain displacement theory, where we are cutting the higher order features of the strain. Remember, we are cutting the strain distribution of higher order. When we are going to the one carbon strain displacement theory, we are now going to the square term of strain and higher order considerations. It all depends on us. As I told you that in nonlinear, see the square is there. We all know from the algebra, when we are analyzing any square part, we have two equilibrium points, two eigenvalues. So both are even satisfying the conditions. So which one is correct one? Because both are eigenvalues, both are satisfied, the equilibrium point satisfying the equations. So square term, higher order, if you look at the Taylor expansion, we can go up to any, the higher order features, the polynomial features, square, cube, and fourth order. So the one carbon says that we need to consider the square term of strain with the displacement relation. So that's how you see now the geometry. We all know that the strain is even the tensor part, and now we are going for the square term of the strain along with UVW. So this is the nonlinear geometry compatibility features. So we can choose either linear and nonlinear, and then we are applying the Hamiltonian. So there are, you see here, the we can go to the Newtonian mechanics based on the force. We can, since here we are basically trying to relate here the microstructural variation. So the Lagrangian and the Hamiltonian principles are acceptable. So we can consider all UVW, like the displacement, and then you see here how the constraint conditions are being applicable and how they are being composed of. So we'll go, and then you see here when we are going to the linear, then obviously we have 5 linear governing differential equations. So now these, since it's a plate theory, it's a continuous structure, so the differential equations are partial derivatives. So now you see here, we have partial differential equations. If linear, then they are linearly behaving. We can go to the nonlinear. So in the nonlinear, now there is one condition which has to satisfy prior to move further is the Airy stress function. This is basically defining that how you see these satisfying conditions are there of the constitutive relations, because now we are going to the nonlinear way. So prior to go to that, we need to first satisfy the Airy stress function. We need to check, and then you look at that. Even after putting that, once it is satisfied, now we are going to see that how many now the nonlinear parameters which are governing the entire phenomena using the differential equations. And once we do that, we need to first see the strain, because as we know that the strain is having higher order. So what is the strain compatibility equation? That has to be a constrained part. So this is where you see the combination of this. That's why you see here, I kept it on the green. This is what our main mathematical significance to justify the physical phenomena happening in the plate. Once you do the problem formulation, now there are lots of solutions. The easiest one is using ANSYS. People have used the ANSYS because it's a inbuilt software, commercial software. They solved it without having any logic, and then they are simply doing. This is one of the BTech level project people are doing, and they are doing. The important part, because we all know that this finite element method is an approximate method, is a discretized method where approximations happening at each and every state function. We don't know that, you see, whether FSDT and HSDTs are accurately mapped or not there, because you see here the inbuilt functions are sometimes not compatible. Because we generally they are saying we have exponential law, power law. In the sigmoid law, they are also showing various inaccuracy. So then you see the things come up that analytical solutions. So analytical solution, as Ramanujan started from the Indian domain, so analytical solutions are giving the exact solution, the accuracy, and the precision is there. Remember, the accuracy and precision both are very important when we are going to the analytical solutions. So we can go to both the linear. So this is, you see, the Galerkin-Vlasov method. which is a semi-analytical solutions are there in the, and then we can go to the Galerkin method as well for the non-linear. We can find out, you see here, the five linear equation of motion. We can get the mass and stiffness matrices through analytical one, and then we can compute the linear displacement, stress, frequency, buckling, means whether we are going static, whether we are going dynamic part. And then these are the model frequency. The model analysis is basically a free vibration analysis. Sometimes people are even, I'm asking in various the exam, why we are doing model? What is the model frequency? We all know the natural frequency. We all know the excitance frequency. But what do you mean by the model? Why we are doing model analysis? Because model analysis is simply representing the free vibration. And in this world, there is no any concept called free vibration. It's a forced vibration until unless if there is no interfacing of the system to surrounding. No system can be excited except the human feelings, because human feelings are somewhat internally excited system. So anyway, our human heart or human brains where the excitations are happening within that. But generally you see here the mechanical systems are not being excited without that. But to see the inherent character, the responsive character of any system against the excitation, we need to first find out that what exactly its real behavior against the system, against the force. So we need to excite and then we need to see. We need to remain absent during its pattern, during its behavior against that force or against that action. So that's why model frequencies, the natural frequencies, the eigenvalues, there are so many things you see here. They are simply showing its equilibrium condition feature, that this is where the points where the systems are showing equilibrium nature, and these are basically my exciting frequency because they are falling under dynamic action. When you are going to now the nonlinear part, as I told you that you see after array function we are satisfying 2D condition. Array functions are basically in two-dimensional. So once you can satisfy the 2D conditions, the three nonlinear equations are being derived of, and then you see we need to solve. So we can go with the static, we can solve, and we can get like the displacement under static part. You see here the buckling and all. But when we are going to the dynamic, either we can go to the higher order of Rangakuta method, or we can go to the harmonic balance, that how the excitation, the simple harmonic motion excitation is there, and then how harmonically we can analyze, you see, the excitation pattern. So we can go to anything, you see, we can go to the time response, we can go to the frequency response. So whenever we are doing any dynamic analysis, there are two broader categories responses are there. One is the time domain, where the displacement, velocity, acceleration variations are happening in the time variation and incremental time. Or we can go to the frequency excitation, that what exactly the peak of excitation is there and what is, like the variations are being happening. This is what you see the since now. This is the dynamics. So now in basis of that, we are coming to our main problem, the modeling of sandwich plate, where you see the property variations are like that. And when we are going to this, there are, you see, the four cases which were considered here. The type A, where you see the thickness variation property considered here, and this type B, where here from H1, this is HM is the mean. So from mean to this, from mean to this, and from mean to this, you see here, these are basically the sigmoid part. So what we have, if you look at the let me show you that here. So with this property, the P you see here, 0 to 10, these are the variations. So for type A, if you look at, you see here, from mean to top and from mean to bottom, you see here, the variations are happening, and this is what the variation. So in between H0 to HM, this is where, and from H1 to HM, these things are there. Now we are going to the middle one. Look at the distribution, how the properties are distributing along the thickness variation. This is what it is. So on top, we have this one. On bottom, we have this one. 0 and 1 are simply representing one type of material that we have, say, ceramic, and we have, you see, the metal. But in between now, this is what the sandwich structure is showing the variation. The hard material. In the hard material now, the properties are varying at the top core and bottom core. The middle one is absolutely uniform. So say we have FGM, functionally graded material on top and bottom, and we have, you see here, a constant part. Say some ceramic is there, in which you see here, or some part is there, which is not being varying with that. The soft material, because now the core is also showing that part. So here we have this part. So either side, you see here, either the hard and soft core, that what exactly you see, the Young's modulus variations are being considered with that. We are simply using that. So in that, you see here, one of my PhD student, he is now the faculty. So he it was a part of his PhD. So we have done it. In that, you see here, when we are really configuring that, The two important parameters are there. Without that, you see here, our analysis is almost weak. The porosity, whenever we are fabricating that, the porosity is always there. Perfect, the perfect cannot be obtained. So the porosity of anything, so either P1, P2, P3, these types of porosity variations are there. We can mathematically map, you see here, this. And then you see here, the another part is the thermal distribution. From you see 0 degree Kelvin to 600 degree Kelvin, this is where you see the variations are happening. So we need to consider both the effect together to analyze that. The porosity, what type of porosities are there, and how you see the properties are being varying. The P0 part is basically varying. Along with that, we need to consider. So this is what the things are. And then when you are considering the temperature, the thermal gradient, we can go to 1D because you see the main thickness variation, the temperature is varying. So we can say it is 1D steady state. You can go on a steady feature also with adding some kind of void or with adding anything you see here there itself. So the equation can be modified with the constant and the temperature variation towards the thickness direction in the FGM and SFGM field, means the sandwich SFGM and sigmoid this functionally graded material. So this is where you see the temperature variation, and then you see here the temperature variation towards that the functions are being considered. This is the gradient feature of that. So these are some of you see like even in that right now we are again assuming that there is no heat source within that. So without heat source, this is one of the common we can say 1D the steady state heat conduction equation. Again, remember, since we people are talking about the microstructural behavior, conduction is the only representation there because we are assuming that the temperature is varying through the molecular through the molecules, and that's why you see it is a molecular transformation of that. So from here TB1 to, if you are going to the top of one, that is you see the this TT2, all that part is being considered. So according to what functions which I shown you, the type 1, type 2, type 3, type 4, ABCD, we can consider these temperature gradients. So this is what you see. It is being like analyzed first, that when we are choosing what properties you see here, whether we are going to this or whether we are going to type 2, we can go that the temperature, the change in temperature 0 degree Kelvin, when both sides there is no temperature gradient. But when we have the temperature gradient of 100 degree and when we have the temperature gradient of 300 degree Kelvin, how the actual properties are being varying. And this is what the realistic phenomena. So now our problem domain is thermomechanical, means there is the thermal load is there and there is the mechanical loading is there. So thermomechanical features are very important as far as the functionally graded material is concerned. The another part, since now here say we are in the domain 1 case, the higher order shear deformation theory is considered, where the shape function is being varying this one. So now you see here, we have, you see, there are two main foundations are there. The this Pasternak foundation is there, and another one is the Wrinkler foundations are there. Anything can be considered. Why these considered? Because you see the shear layer is very sensitive to whatever the domain which is coming out from that. This is very important. So anything, either we are going to any kind of that, there are parameters through which we can define the constraint condition of this foundation, because they are providing our main, we can say, the flexibility domain there itself. So we can define the constitutive relations in the stress. So we have stress and corresponding strain. So this is there, and then this is what the happening of this. So we can simply find out these main coefficient based on the material parameter. So this is Q1, Q2, like the Young's modulus, which is being varying with the Z and temperature dependent. And then you see this is what my Poisson ratio is there. So we are simply considering these variation for our problem formulation. In the higher order shear deformation, where this deformation in which you see both, since it is a dynamic, so we have XY, the space domain, and the time domain, the variation. And this is being driven by this f of h, then hyperbolic and this. So look at that previously I shown you the shape function of various. This is what the function which is being considered here in this study, in which you see the r square is also being considered. So we have, you see, like not only this z by h, but this r, that towards you see the domain, there is, you see, the parabolic variation, the nonlinear variation. Yeah. So we need to check it out. We need to check it out, the convergence feature with the compatibility of our domain there itself. So now you see here, when we are formulating the problem, this is what the strain relationship, which is, you see, the initial, then driven by, you see, the like the transverse direction, and then the shape function. So altogether, you see here the strain conditions are happening undeformed, then in the deformation towards that, and then you see the angular, because you see here we have, you see the r square. So what exactly the angular strain features are there? And when, as I told you, that Hamiltonian principles are being acted towards the displacement part, so we can consider all this, that how the variations are being happening. The time is not there, otherwise you see here that can be even discussed. So this is how you see the mathematical functions are being derived, or for linear right now. For non-linearity, there are changes in the compatibility conditions of that. So that is what they are. So we can define the governing differential equations. So this is what our governing differential equations are. They are using, like the Hamiltonian principle. When you integrate that, and when we are simply getting the derivatives, this is what, like the derivative features are there of the governing differential equations, and all that part, like the coefficients, they are being, like derived from these constraint features. So this is the composed of that one you see here. Similarly, nonlinear equations can be also derived there, and that can be also, like get the strain compatibility, these, like the straight resultant, and then you see here the entire equations can be formed. And if you look at that, they are of this higher order. Right. So even you see here lots of constraint conditions with the shape function in x direction, y direction, the strain conditions you see here, like all that can be computed. The boundary conditions. There are three boundary conditions can be obtained as far as the plate is concerned. Simply supported. So this is all the simply supported conditions are there. Second, the clamped condition we have. So we have S, simply supported, clamped, and free. So either we can say, like we can put any end to free, we can put any end of the plate, four end you see here with the clamped or these things. So towards x direction, towards y direction, because in the z direction we are evaluating our main function. So this is there, and these are basically the conditions for our solution. So you see here the static solution, which we can find out. The free vibration can be get, you see here means the free vibration means for the modal analysis, we can get the natural frequency omega. We can go to the buckling and we can go to the thermobuckling, you see here, where this condition, the stiffness variation is there. We can get the mass matrix. So this is what the mass matrix and the stiffness matrix, along with what exactly our requirement is. The important part here in any of these analysis, that what conditions are being there. So every, if you look at that, these are being subjected by these conditions. So under static, free vibration, buckling, or we can say under thermomechanical loading, that can be evaluated. Post vibration, even we can go to anything. So these are the examples which were taken, you see here, because like in that lots of things are there. So we can like simply check it out, that under any load application, what is the things which are being considered. So we have, you see here, the matrix, and whatever you see the ceramic. So metal to ceramic, these are basically, if you look at the properties, they are being varying, and you see the parameters can be evaluated. So these parameters, if you look at kw and kp, the Winkler and the Pasternak, they are basically the foundation parameters. And this is what you see, like that how the distribution is happening with like the this, we can say, our metal part, the Young's modulus, and you see this is what our thickness variation. So if you look at, it is not only varying from like the feature, this h cube cubic variations are being happening, and this is what it is. Because until unless we are not going for the higher order, we cannot evaluate the real distribution. So this is what you see, the normal distribution, and this is the transverse distribution under three conditions. The simply supported, all simply supported constraint, all boundaries. We have, you see, the clamped condition, and then you see all simply supported, clamp to simply supported. So anywhere you see here, whenever we are considering, the stress distributions are there under different temperature. Because as I told you, that we can go with the defect free, means no porosity, and defect with the porosity, but temperature is one of the essential conditions. So it is like that. So then you see here, even we can simply plot these things, that how you see under these all the six conditions. So this is now it is showing the six condition, all simply supported to all clamped condition. And how you see the distress, the stresses, and the displacement. If you look at that, there are 2 points, A and B, and then the stress. This is what exactly my aspect ratio in A and B side, and what is the stress distributions are there. That. So this is one kind of presentation. But the main presentation, and then even you can say, we can find out the eigenvalue, the free vibration for the polynomial, for, you see, sorry, the power law and the sigmoid law, you see the variations there itself. So even free vibration, or even under the buckling, where you see how the frequency and how you see the critical load variations are there, that can be also checked. Only I'm showing right now. But the main part is coming, because this was the how much time, I don't know. Professor Bhaskar, can you tell me how much time is there? Hello. Yeah, how much time is left? 10 to 15. Oh, that's wonderful. Then it's good. So now you see, when we people are talking about the forced vibration, then there are tools. There are tools which are very important, like under the dynamic conditions. As I told, the time displacement, which is very important. Time displacement is simply we are saying, the simple variation which we are simply considering in our 10 plus 2 or our BTech level, that the velocity distribution is there, the displacement distribution is there, acceleration distributions are there, force distribution, torque distribution, like that. But that is not, you see, giving the significant feature of the responses. We can say, okay, oh, this is a periodic, this is aperiodic, this is quasi-periodic, this is subharmonic, this is superharmonic. That can be only say. But if somebody is looking for the physics of that, then that cannot be found out. So that in that case, you see here, we need to go to the signal processing tools to analyze this nonlinearity in that. So that is the phase trajectory. The phase trajectory, you might have also listened the phase plots. So in that, you see here, we can simply say that since it is a dynamic phenomena is happening, so what is the relation between the driven part, means the displacement and its derivative, velocity and its derivative acceleration. So that is very important because that is giving that how the phase is changing during the dynamic action. And accordingly, we can find out that what this motion is saying, what this dynamic phenomena is saying, whether it's periodic or falling in aperiodic. And in aperiodic, what is my center? Like you see, when we are rolling our hand, we all know that you see here, when our center, that is a loci, or that is, we can say, our this stable point, fx, when you rotate that, the entire periphery is depending on this initial condition. You change anything, maybe you see the circle can be changed into elliptical or any other structure. So that is the phase trajectory, because that is showing, you see, the phase itself, that how actually these dynamic parameters, the derivative features there, how they are being related. Then Poincare map, this is another part. So you see here, when you are going to this is what first is the time displacement, very common. You look at that, the periodic to subharmonic to quasi periodic to onset of chaos to now you see here the beat phenomena. So all the phenomena is absolutely being mapped out. But if I would say that now under this, whether this is a noise or this is a defect, we don't know. We can't say. And what is the frequency of that? Because at on top and on bottom side, we have a dense band frequency spectrum. Even if you look at that, now this peak, the clear peak of excitation started bifurcating. So this is the beauty of, you see, like the signal processing, that on the time domain, when we cannot analyze those things, we need to go to that. So this is where you see the another part is the phase trajectory. If you look at that now, you know that this is my only one point of attractor, that strange attractor, and the entire periphery is being there. Here now we have two energy domain, one and this, that means the two waves are there, they are being mapped up. And that's why you see here the things are. You might have heard about the FM radio or AM radio or radio frequencies particular. The FM is frequency modulation. So how the modulations are happening? Now, the 50 hertz carrier frequency, 50 hertz is mapping frequency. So the modulation happening at these two, and what is the resultant? 89.2, 92.4 FM radio. So how the modulations are happening? This is where the things are. At what phase? At what phase the angle is there? So that's why if you look at in each and every part, which are leading from periodic to quasi-periodic, this is quasi-periodic, and to chaotic, where the randomness is there, everything can be analyzed using that. And then finally, this part, the Poincare maps, because sometimes even we don't know in this chaos, if you look at how many actually irregular points are there. Through this now, we can get so periodic 1T, 2T. Now here you see we have multi-periodic, and then even the deterministic phenomena is there. So this is multi-periodic. We can say like the quasi phenomena. This is the chaotic one. So here we are simply putting a set. Henry Poincare was there, the French guy. He devised this technique, and this is very popular for nonlinear structural analysis. Nonlinear analysis, I would say, signal analysis. So now you see, coming back to our using these tools, and another one is the frequency FFT, the fast Fourier transformation, the transformation function. So FFT is basically one of the important technique. Other than time domain, all that which we discussed in the previous case, the frequency pattern is also very important. From there, you see, at least we can say that what exactly the excitation pattern is. 2, 3, more than that, you see. So now here we can say the SFGM feature is there, in which you see the sandwich part is also there, and it is being driven by the sigmoid law. We have, you see, now the displacement towards, you see, the transverse direction in the time domain. When we are changing, you see here only the load amplitude. If you look at the load, right from 10 megapascal, all other parameters are same. Constraint conditions are same. The material properties uniformly distributed. You look at that how sensitive it is. Right from the quasi-periodic phenomena to chaotic, the things are now almost changing. So that's how the sensitivity is. So even the load variation is there, the pattern of the plate is absolutely being changed because of its sensitivity. When you change, you see the span to thickness ratio. That's what our main part, the aspect feature. Under you see the, like we can say we are considering the KW and KP, which was the foundation part within that. We have, you see, the KW0 and KP is varying from in one direction one, and the other two directions are even the similar unit part, but in the minus one. So when you are changing, we have absolutely, see here, when you look at that, by A by H5 to A by H100, almost drastic change. Quasi-periodic means somewhere it is falling in the beat phenomena, well-structured pattern of the phase plot, and then Poincare, they are all well-behaved. You see, outer periphery is almost in a specified geometry, but here now they are absolutely changing. So that's what you see the things are under these conditions, under the forced vibration you see here, and when you are considering like the configuration the same, only just changing the aspect ratio, the entire dynamic behavior is changing. Even you see here when you are considering like the other part, other aspect ratio of that A by S to 10, there was, you see here, like this 5 and 100. When we are changing that, and with this particular part you see here now, this is, you see, no chaos, but we have even from quasi periodic to now it is coming back to the periodicity, the multi-loop periodicity. Means, you see here, each and every loop has its confined, like the space. So phases are basically the confined part. So we have multi-periodic features. So this is what it is, you see here. With putting the constraint part here, we can simply brought back this from A by, just you see here, we have A by H, only we are changing B by A zero point 0.5 to B by A. Means, you see the other two aspect of this, B and A, the plate part, we have this one, you see here. The length and the width part, you see. Sorry, the length, and then other B is the thickness part. Frequency domain, which is very important since we are using both Wrangler and Pasternak foundation. Here this is there, that when we are simply changing the constraint conditions, means the Wrangler 0 to, you see, this part, by keeping the Pasternak feature constant, or when we are changing that, how the frequency excitation patterns are changing. This frequency is the non-dimensional frequency, please remember here. So we have, you see here, this is what it is. So this is what we can say the deflection pattern means, like the W by H, how it is changing with the frequency part in this way. Or even when we are changing this, you look at that, the configuration. 101 means on the top core, type A, type B, type C, if you remember correctly, then we have 101 means the properties varying here. Now here the properties are being changing. So when they are being changing, you see here with the different cores in the sigmoid part, how the frequency excitations are being changed. This is very important because you see here, this will suit according to our applications. And then we can also see the thermomechanical load for that. So with the temperature change, the things are being totally changing, you see here, about the load. So which load, and according to what type of deflection we are interested, we can go to apply the temperature, and accordingly, you see here, the things are being varied. So here we are using the zirconium oxide, that is the ceramic part, and this is stainless steel of austenite part, SUS 304. This is absolutely using in our like the BRC, because this was a BRC project, so we did it that part. So under that, you see here, that can be used. So this, like for atomic feature, this is very important. This is the entire analysis, only I'm right now showing this part. And then accordingly under thermal environment, where you see the temperature is being changing, that this is the delta K 100 Kelvin, the things are being, like A by H 5 to 10, how these variations are their dynamic phenomena. And then you see here, when we are going to 300 Kelvin, drastically changes are there. So that you see very important, that where you see the like we can say the concentration of the motion is there, how the attractors are being there, how many other attractors are being formed there, and the chaotic phenomena, this is being there. Then we can go to the ceramic to P by 2, you see the volume fractions of that, and then we can get, so by keeping these constant, we can simply get that how the variations are being there in time domain to phase trajectory to Poincare map. So this is where you see, like at we can say the previous the 100-degree Kelvin, the 300-degree Kelvin that can be derived of. So this is what the overall feature that under thermomechanical loading, what is the change in the pattern of dynamic pattern of that right from 0-degree Kelvin to 600-degree Kelvin of temperature difference. So you see that even we are not changing any mechanical loading, only and we are not even we are putting every condition constant there. There is a drastic change in the behavior. These loops, when there is no actually the temperature gradient is almost remains same. We have a well patterned behavior. You see, even the attractor is also having like the stable feature. But when we are moving towards that, they are absolutely being diverted. So this deflection pattern is evolved, you see, in a very different way when you are changing the temperature, and that is quite obvious. But important part here is the ceramic and the metallic feature, they are behaving in a very different way together. So this is what it is. So thank you guys. So this is the today's lecture, and these are few publications anyway. So this was there, you see, various publications are there from this Simran, actually Simranjit Singh, and thank you very much. So this is all about. Thank you. Thank you, ma'am. Thanks for the invitation. Thanks for now I'm here. If you have any query, please, 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 please. Functionally graded material, as the name itself speaks, in that you see here, as I told you that it has two different type of materials. One side say we have metallic feature, one side we have ceramic feature. Now, if I am saying that my application is of thermal, inside I have more than 100 degrees Celsius, the metal may behave in a very different way. Then I need to put the ceramic. But at the same time, you see an outside where you see here we just want to avoid that part, so we can put even the other side of metal. So in lots of application where the we have two different type of opposite almost type of functions are there, just like as I told you that the teeth is there. On one side we need to cut, we need to shear, put something, and on the other side we need to bake some kind of damping. So by one material, if I'm just using say steel, or if I'm using composite, that cannot be get. So the functionally graded means one type of function is being graded from one base to other base. So this is what the functionally graded upgradation of any property along with thickness direction. This is functionally graded. Material nonlinearity is a kind of non-homogeneity. Because you see, like any material, like if I'm using say steel at very normal temperature, it's a homogeneous feature, isotropic feature which we are considering. It's a linear. When you apply the load, all the FCC, BCC kind of whatever the domain is there, they will behave uniformly. This is, you see, the force and deformation with the material constitutive. But when we are going to the realistic phenomena, we all know that the material cannot be linearly behave. The strain, again, remember, you see here we are talking about the strain relationship, that how the strains are happening when we apply the load. So generally, you see, like our BTEC level or our normal consideration, we are saying the stress strain relationship is linearly behaving, because you see the Young's modulus is there. So we are confining that relation within the elasticity. But in actual, this is not there. So material nonlinearity means the material composition is like behaving in a very nonlinear way according to the load application. And that's where the composite is. The heterogeneous, non-homogeneous, any feature, they're all material nonlinear. Yeah, please. Software is free. Again, don't use ANSYS. ANSYS, if you want to do the research in that, ANSYS is one of the worst software for this. People who are doing, if you want to do the research, if you want to guide to your BTEC level student, just give in the ANSYS, they will create that and the ANSYS. So finite element software is there, one which is of BTEC level. If you wish to do now this for modeling and for simulation, for realistic part, then you need to use either MATLAB or any software, or like mat free, or lots of, you see, mathematical equation softwares are there which you can use to solve these equations. or you can go with the massless methods, mass free methods are there. You can go with the extended finite element method. You can go with the XIZ. Lots of, like the boundary element methods. Lots of methods are there. The computational tools are there which can be used. The porosity is basically defect. If you look at the casting part, the porosity is quite obvious, because when we are doing, like with the molding, and when we are doing the processing, any processing, there is, you see. So if we know that now this is the porosity, because here, if you look at the nature of this material, we have one side is ceramic and one side is metallic, and there is a property distribution along the thickness. So porosity is there. Now we need to check it out, the porosity. There are, you see, the NDT techniques are there, but we need to see the distribution. Here is important that, okay, we have a void, we have any kind of defect, and that is creating some kind of porosity feature because of some moisture or anything is there. We need to now, during the process, we need to check it out, that you see here whether the porosity is there. And when the porosity is there because of the material composition, we need to check it out, that using NDT technique, basically it is being measured. But important part here is the distribution, how the porosity distribution is there along the thickness direction within the material domain. That is more important. Simply supported, or like simply the clamped conditions, the constraint conditions, they are all the holonomic conditions. Simply supported, so all sides simply supported, so one type of motion is being allowed. You see here we have, you see, like uh, there are basically, if you go to that, the joint, there are two main joint, one is the prismatic and one is the rotary joint. So simply supported, which joint we are using, this is a simple, very simple part. So the clamp condition, the constraint condition, so here the deflection and the derivative of deflection is how we can derive. As simple as that. You see here we need to put these conditions, that what exactly the shape function is to be distributed all along the constraint condition. So right from four SS, all four simply support point, you see here, that how much, you see here, this, like the deflections are being allowed there. As such, you see here, the what was the other another one? Now in that, one is, you were saying that simply supported, and what was the other? Okay, was this the question or something else? They are all constraint conditions. So the geometry, basically, like this is the kinematic constraint condition. Whenever we are allowing something, say if I'm saying fixed beam, so say beam, let us say very simple thing. Fixed beam means now the constraint condition, both beam ends are fixed. So certainly you see here, like the constraint conditions are defining that now here we cannot allow anything to be displaced out. So outplane this displacement is not being allowed. Fixed. Now I'm saying simply supported beam. Now that means, you see here, there is a turning joint, and then you see here that is being allowed. So simply here also, since we are constraining the conditions by the four side of plate. So we are saying, you see, this side simply supported part, this side. So whenever we are doing, you see, like the solving, we need to give the initial condition. There are two main part here for any solution: the initial condition and boundary conditions. So initial condition, that now initially what is the condition, and then boundary, during the load application, how boundaries are being allowed, whether they are allowing in plane strain, whether they are allowing out plane strain, because the strain is very important, because they are basically driving your displacement feature. So this is how we are considering the conditions. Please. What are the possible processing technique? Okay, so you see here, yeah, we can go right from our this the powder metallurgy. The powder metallurgy is one of the races, because you see here we need to first create that, and then accordingly, you see here, under the this environment, we can say the CVD technique, we people are generally producing according to what type of thickness and what is our arrangement, we can go. And nowadays even it's very simple. If you are going in the domain of our the simple material, I mean to say that, not like tungsten and all other part, even 3D printings are there. People are just using 3D printing to get the things done. So there are lots of processings are there, right from metallurgical aspect to our main final shape. We can go from powder metallurgy to CVD to 3D printing. Lots of techniques are there. Application of functionally graded material. yeah, it is. Oh, it is wonderful. Like you see here, as I told you that this wherever the plates are there. Initially, you see, we were using the plates for various things. Now they are using the functionally graded part because even for the space structures, even for our any kind of structures, you please go to internet, you'll find lots of applications nowadays. Wherever you see earlier the laminate plates were using, now it has been totally replaced by functionally graded material. Because in the laminate plated, the plates or anywhere you see here, like these things were happening because there were you see here in the when segmental features there is some like the confined features are there means if the two plates are there laminate features here we have always some kind of problem, the shearing phenomena, the bend during the banding, during all that part you see even under the impact loading also, this is one of the worst part was there. So nowadays the functionally graded materials are absolutely being using. Important part here is not the FGM. In that you see here how the damping features are being involved there. Because even say simple example now I just want to put the shell like in like say my turbo machinery is there or like my boiler is there, so where you see, I just want to put the, like the casing, or even you see the rotor casings are there, internal or outer features are there. I just want to see that now inside is a huge temperature and you see the huge dynamic forces are coming. I will go and put the metal and outside I will put the ceramic so that the temperature or whatever the things which are coming, because inside we all know that in turbo generator or in even you see the like the total rotor unit IP means the intermediate pressure, high pressure or whatever you see here, inside the steam pressure is almost 700 degrees Celsius. So we need to avoid that interfacing. So earlier we used to have you see the high thicker part. Now within the specified feature, like we can use this. So this is wonderful. Lots of application. I would say like even for our like the bones particular means forget about the mechanical, even in biocompatibility, they are absolutely being used. So this is what the things are. Yes. Yeah, absolutely. Actually, because this is the beautiful thing you see here. Because actually, what do you mean by a sense? Now here the sensors are of various nature. Say if I just want to see that now the displacement occurs, if this displacement can be converted to the voltage, now you see you have either by using anything you see here, now whatever the voltage changes with the displacement, we can simply sense that now this much force is being applied and this much deformation happens and this much voltage, just like in piezo. FGM is because like when you are sending anything to the space, there you see we need to have proper control on the movement. So even various robotic arm, like the industrial robot, the robotic arm, and even the joints, because you see here somewhere we need to put some constraint conditions. These are being also now using this FGM. People are using that. So there are lots of applications. Application wise, there are like various things, sensors, and then corresponding the drives, means the actuator. What how much you see the actuation is happening, as you might have seen in that it's a well controlled actuation in particular direction. Say if we just want to actuate in one direction, like you see, say it is going in X direction or in thickness direction or anything you see here, we can define that constraint and we can have a proper actuation. Because in actuation, the important part is it has to have the accuracy and precision that can be maintained there. So sometimes the sensors are always giving some kind of like they are not precise, they are not having the repeatability feature. So this FGM is providing that kind of additional features there itself. Sandwich actually, because like here we just want to add certain property. In FGM, it is if you look at that, the total matrices were varying across the thickness. So here we have you see the composition of one part and their part. But here the sandwich part is giving you an additional feature that you don't have to put all the property together. You just want to add certain property within the structure itself. You can put that section, you advance that section because this is the advancement. Because you are giving some additional property within the structure itself along your neutral plane or the mid plane. So you can put just like you see, I've shown you type A, B, C, D, soft or hardcore. There we were adding only some additional feature within the section of that part. Instead of giving the entire feature, we can modify that along with the FGM. So FGM is a content structure from one property to another property. Sandwich functions are being added to modify certain property within that. So this was, you see, the main. advancement of sandwich feature within the FGM plate. Natural frequency is the inherent character. Remember, natural frequency is always there. For any system, there is a natural frequency. To control the vibration, we don't need the natural frequency. Actually, it is if you do the model analysis. Again, this is a vibration problem. When you have the model analysis, you have two things: the eigenvalue and eigenvector. The eigenvalue is showing the natural frequency, but the eigenvector is showing the relative displacement of the entire structure because they are eigenvectors, how they are being varied. To apply the control law, we are basically going with eigenvectors, not the eigenvalue, because the eigenvectors are happening at the natural frequency. If you go to this structure, how many natural frequencies are there? Infinite. How many degrees of freedom you are choosing according to the natural frequencies are there? So if I am saying, you see here, say at my first natural frequency, this is what my pattern is. Now I need to configure that the sandwich structure to control that relative displacement of that entire structure. So control aspect is always being derived out not from natural frequency, from mode shapes, the eigenvectors. All right. Thank you. Thank you very much. So now, should I no, that's very good. Actually, I'm really happy because this call was from MBM, and I mentioned in my mail that this is my alpha matter. I did my most of things from MBM, so and that too I'm from Jaipur. So thank you very much for inviting me, and thank you very much for an interaction. Thank you. Should I leave now?
Thank you.
Oh, thank you, thank you, thank you very much.
Thank you so much, sir. Your words of wisdom have left an indelible mark on us and have defined the paths that we would follow in our training program. I request the next speaker of the morning, that is our second eminent speaker, Dr. S. Pradyuman. Dr. Pradyuman is currently working as an associate professor in the Department of Applied Mechanics since December 2016. He joined the Indian Institute of Technology, Delhi, as an assistant professor in May 2010. Dr. S. Pradyuman received his PhD in civil engineering from Indian Institute of Technology, Kharagpur in 2009 and MTech from Vishweshwarya Technological University, Karnataka. He has received his BE. Yes, ma'am. Yes, ma'am. Okay, ma'am. Yes, ma'am.
Yeah, am I audible? Good morning. Yeah. How many participants do you have? Two- 200. Okay. Are all these 200 participants are attending? Okay.
Now, I would like to invite our second eminent speaker for the morning, Dr. S. Pradyuman. Dr. Pradyuman is working as Associate Professor in the Department of Applied Mechanics since December 2016. He joined the Indian Institute of Technology, Delhi, as an assistant professor in May 2010. Dr. S. Pradyuman received his PhD in civil engineering from the Indian Institute of Technology, Kharagpur in 2009. MTech from Vishweshwarya Technological University, Karnataka. He has received his BE from Mysore University. His areas of interest include dynamics and stability of plates and shells, finite element method, meshless methods, composite structures, and functionally graded materials. He has more than 12 golden years of teaching experience and has published and presented more than 50 papers in peer reviewed and international journals and conferences. He has been referee for international journals like Composite Structures, Thin Wall Structures, and International Journal of Mechanical Sciences, etc. Sir, we are blessed to have you and an experienced mentor like you with us today in this session. I request you to kindly take us now on the journey on the composite mechanics and bless us with your in depth knowledge on the same.
Thank you. Can you see the screen? I have shared the screen.
Yes, sir.
Okay. Okay. Uh, Thank you very much for giving me this. Am I audible? Please let me know if there is some issue with my voice or the video or anything. Okay. Thank you for the invitation, Dr. Emrati, for inviting me to deliver a lecture on mechanics of composite structures or mechanics of composite materials in this faculty development program. So I feel it's good to know many things during this time of pandemic. Okay, I'll start my yeah. I'll start my. Shall I start now? Okay, okay then. So the topic is mechanics of composite structures. As you know, today is the first day you are attending this faculty program, the lecture program. And I'll start with some basic introduction to the composite materials and the mechanics of these materials and how they are useful and how to deal with different aspects of mechanics in this. Okay, so let us start with what is a composite material. Composite materials, as you know, it consists of a combination of materials. So they are mixed together to achieve specific structural properties. So you mix two materials to get a composite material. It's not like it should not be confused with with alloys, where alloys you make a microscopically they are arranged and you make a homogeneous kind of metal from two different metals. But in this case, we take two different set of materials and they are bonded together to make a composite material, and we can achieve some specific structural properties which is not possible with the single material in that combination. So the properties of these materials are superior to the properties of the individual materials from which it is constructed. So therefore, we can get a much superior material when we combine two different materials. So that's why we go for the composite materials. Widely use these materials in automobile, aerospace, civil, and medical applications. So you name any industrial application with engineering background, so we use these composite materials, right? So why do we use the composites? What are the benefits of the composites? So we know that it is cost effective. It doesn't mean it's cheap. It's cost effective is in a different sense. We can reduce weight using the composite materials. Weight reduction is one aspect which gives us the advantage. Strength and stiffness, for the lesser weight, we can achieve the same strength and stiffness compared to any metallic structure. So we can achieve some good strength and good stiffness for a lower weight. And it provides corrosion and wear resistance, fatigue life, and thermal and acoustic insulation. So therefore, these materials are widely used in different engineering applications. And we can go for tailored surface. So in that case, what we can do is, depending on what type of surface finish we want or what type of strength or stiffness we want, based on that we can go for the this material, right? So uh, am I audible? There was some issue, I think. Yeah. Okay. There was some disconnection, or I don't know what happened. It was freezed. Okay, I'll continue. Uh, so therefore, we go for composite materials due to the advantages listed in this slide. However, there are a lot of limitations when you come across with this kind of composite structures. One, the high cost of raw materials. When you just look at the price of carbon fiber or resins, they are expensive. So therefore, for example, if you want to buy 1 kg of steel or 1 kg of carbon fiber, they are more expensive. So, but you can minimize this cost by using you can get a good strength or good stiffness for a lower weight. So therefore, this limitation can be minimized. Okay. Then composites are more brittle compared to any metals. So because of the brittleness of this material, there are a lot of disadvantages. So it breaks suddenly, and you don't get enough time to rectify the mistake or repair the problem. Then it will be a problem. So therefore, composites are more brittle compared to metals. So their transverse properties may be weak. The fibers, for example, have a very high strength in the axial direction, but they are weak in the transverse properties. Matrix is weaker. Therefore, we what we do is we take some fibers and mix it with the matrix, and the matrix is very weak. Therefore, it provides low toughness. Reuse is very difficult. Repair introduces new problems because it introduces some skills for repairing the composite structures compared to any metallic with bolt nut connection. Some with reasonable training one can do, but for doing repairing for the composite structures, you require a skill set, and also you require some set of instrumentation also. Therefore, that is one limitation. So The materials require refrigerated transport and storage. That is one problem. And the next is to get hot curing is necessary in many cases, requiring special tooling. And environmental degradation is one big aspect because the matrix is subjected to degradation so often. For example, when it is subjected to a very high temperature, it is subjected to fire, it's subjected to any kind of moisture, then it undergoes some kind of property degradation. So these are some of the limitations we have. But in spite of all these limitations, people are using composite structures in different engineering applications because the advantages are far more compared to their limitations. So therefore, people prefer composite structures. Some of the pictures I am showing here are for the application of this composite structure. For any aircraft structure nowadays, a lot of components are primarily used with the help of composite structures. Composite structures are widely used in fuselage, wings, and so many other structural components in an aircraft. Not only in aerospace industry, we also use in civil engineering applications, in bridges, in windmills, in many other structural applications. To strengthen the existing structures, we use composite structures. In aeronautical, in marine industry, the submarines, we use it for yachts, we use it for ships and so many other components in the marine industry. In automobile industry, we use for the body of the superfast cars, or the inside components are primarily made from the composite structures. So these are some of the simple applications I have listed. It is used in sports, it is used in medical industry. There are a lot of other applications possible. Okay, so coming to the composites, what are the different types of composites we have? We have fibrous composites. We take different fibers, Kevlar fibers, carbon fibers, glass fibers, and they are bonded together by some matrix. Matrix is some kind of a viscous material where you can keep the fibers and it provides some kind of bonding to the fibers. So that makes the fibrous composites. Laminated composites, you take different layers of materials and then stack on each other. So when it is glued together or it is bonded together, it gives us a laminate. For example, the plywoods we use in doors, we use it in window panes. They are made of laminates. So similar kind of arrangement can also be made for any other laminated composites. Composites is another type of composite where we use particles of different materials and mix it in a matrix and use it as a particulate composite. So these are some major types of composite materials which are widely used in engineering applications. Coming to the stress strain relationship of this, when you go for the stress strain relationship, so you can see that the left side curve shows that it has got some linearly proportional zone, and then it yields, and then it may be the ultimate strength is reached, and that's it. It's kind of a brittle in nature. When you go for the second graph on the right side, so these are actually the stress strain behavior of different fibers: glass, polyethylene, aramid fiber, steel fiber, high strength carbon, boron, and other material. And you can see that there is no yielding, just it takes very large strain and then it breaks for some kind of stress. So you can just get the ultimate strength, and that is a failure strength also. No yielding, just it breaks. So because it's very brittle in nature. Right? So this is a typical stress strain curve. What are the features of fibers? The fibers are primarily used to carry the loads along their longitudinal direction. You know that the fibers are strong in their longitudinal direction, but they are weak in the other two directions, transverse and lateral directions. And the common fibers which are used are aluminum oxide, beryllium, carbon, graphite, glass. There are different kinds of glass fibers, like polyamide. In that, Kevlar is used in defense industries for preparing the Bulletproofing can also be provided using the Kevlar fibers. There are metallic fibers also like steel, titanium, and tungsten, and so many other categories of fibers are available. Now, what is the job of the matrix? The primary job of the matrix is to transfer stresses between the reinforced fibers and protect the fibers from the damages. It may be mechanical or it can be environmental damage. A basic requirement of the matrix is that the strain when it breaks should be larger than the strain of the fiber. It should undergo a very high strain compared to the strain of the fiber. And because of it is subjected to temperature change, the coefficient of thermal expansion of the matrix should be low. And it should also possess good flow characteristics so that it covers all the fiber completely, and there should not be any void, or it should minimize the presence of voids during compacting or the curing process. So this is the characteristics of some of the matrix we use. Okay, let's come to this table where it is shown that, for example, I have listed specific gravity on one side for different materials like graphite fiber, Kevlar fiber, and also listed for steel and aluminum. So 7.8 is the specific gravity. That means it is compared with the density of the water, right? 7 point. So that means 7.8 times heavier than the water. And Young's modulus is a very well-known parameter, so we have also listed here. If you compare the Young's modulus for steel, it is 206 point something, around 200 Pascal. Whereas if you go for fibrous like Kevlar fiber 124 and glass fiber 85 and so on. But when I go for the ratio specific modulus parameter, that is Young's modulus to the mass density ratio, I get now, for example, unidirectional graphite epoxy with E by rho ratio is 0.1131. That means for lesser mass, I can get the same strength when I use this graphite epoxy compared with the steel, for which E by rho ratio is 0.026. It's very less compared to the Young's modulus it gives to the mass density, so or the specific gravity. So that means steel, what we want to say is that it provides very high strength to weight ratio. For getting a very high strength, you need not go for a very heavy structure. So that is the meaning of this. So similarly, I can also draw conclusion from square root of E by rho or cubic root of E by rho. So these are different parameters which are used for specific modulus, and it just says that for lower mass you can achieve the same strength in terms of the Young's modulus or in terms of the other stiffness parameters, whichever you want. So this list provides that particular focus. Okay. Now come to the epoxy. Epoxy is the most commonly used matrix. It has got very high strength, low viscosity, and we want that it should have a very flow rate is to be low, which allow good wetting of fibers and prevent misalignment of fibers during the processing. And low volatility during cure, so it doesn't catch fire very frequently. So it's a very good against fire resistance. It has got low shrink rates to reduce the tendency of gaining large shear stress of the bond between epoxy and its reinforcement. So we can have a lot of varieties of epoxy in any market, so that we can get a good epoxy combined with any kind of glass or epoxy with some good fibers like glass, carbon fiber, and make a very good fibrous composites. Okay. Now, when we are dealing with the mechanics of composites, there are mainly two branches. So we are listing that. One is the micromechanics, in which we study the composite behavior in the microscopic scale. So what we do is we know the properties of the fiber, we know the bulk properties of the matrix. How do we get the combined property of these two? So that actually is obtained from the help of micromechanics. So we get average properties of composite ply from the individual properties of the constituents. We calculate all these things by considering that they act like a homogeneous material. So when you combine the matrix and the fiber, it more or less it behaves like a homogeneous material. So that's what our assumption in micromechanics. Right. The second branch is to study in a macroscopic scale. That is, what is macromechanics? Is to develop the stress-strain relationship for a unidirectional or a bidirectional lamina. Lamina is a set of when you have fibers and matrix make a single layer, it becomes a lamina, and when you stack more than one lamina, it becomes a laminate or laminate. Right. So loads may be applied along any directions, principal direction of symmetry or any off axis. So we have to worry about the loading axis later. So we can develop the relationship between the stiffness, thermal, moisture expansion coefficient, the strength of the angle plies, how to vary the angle. So these things are part of the macro mechanics of the composite structures. Also, we learn about the failure theories of the lamina based on stress or the strength properties of the lamina. Okay, so these are the mainly two branches. One is the micromechanics and there is the macromechanics of the composites. Now let's come to the lamina. So lamina is nothing but it's a basic building block, a flat arrangement of unidirectional fibers or woven fibers combined in a matrix. So there can, if the fibers are placed in only one direction, we call it as unidirectional. If it is woven or if it is bidirectional or if it is a discontinuous fibers, we name it differently like bidirectional, discontinuous fiber, woven fiber, and like that. So one particular block, like a flat block, is what we call it as lamina. So this is the arrangement of a lamina. Laminate is one where we arrange more than one lamina together, or we make it a stack or the bundle of different lamina and make it as a laminate. So in this, we have shown that we have taken four different uh, lamina with 0 degree orientation with respect to the xy axis. Plus theta, we give some angular variation. Theta is equal to 90 degree or any other angle. So we just arrange this, stack together, and we make it as a laminate. And this scheme 0 plus theta 90 and minus theta, we call it as a lamination scheme. So lamination scheme is the arrangement of lamina in a particular laminate. We call it as a lamination scheme. So we can alter the lamination scheme and achieve a lot of properties which can be optimized, which can be tailored to get a specific strength, specific by dynamic characteristics, and so many other things. Okay. Now let's learn about the ply orientation. So why do we arrange the plies in different orientations? Now we have a 0 degree ply orientation. Now, for example, if I am applying a longitudinal loading, axial loading, fibers are very strong in the axial direction. So we apply the load in the longitudinal direction to get a better or the maximum strength. So when we want to carry a longitudinal load, you put the 0 degree ply orientation. 0 degree means in along the same direction in which you are going to apply the longitudinal load. So that provides a better strength. So therefore, we provide 0 ply orientation for the resistance or to carry the longitudinal loading. 90 ply orientation is for transverse loading, and if you put 0 and 90 together, it can carry both longitudinal and transverse loading along x direction and y direction. And if you have plus minus 45 ply orientation, it is for shear loading, right? So we want to have in plane shear, so we can place plus 45 minus 45. So what happens if I have a plus 45 minus 45 ply and you apply the in plane shear? See, these fibers carry the load with the help of tension and compression, because when you say that in plane shear, and if you rotate an element by 45 degree, you get a pure shear case in which in one direction you are applying the tensile stress, another direction you are applying the compressive stress, and which are the magnitude of which is equal to the in plane shears, right? It's TS stress. So the same logic holds good here also, where we apply the in plane shear, and to maximize that effect, we put the plies or the fibers in plus 45 minus 45 perpendicular to each other in that scheme. In plane shear stress is carried as tension and compression in the 45 degree plies. So if you have any warpage of the lamina, you can make it as a symmetric laminate and get the resistance against the warpage and interlamination. So for bending resistance, you know that the near the neutral axis, the stresses are very less, and you have to place the stronger laminates towards the or away from the neutral axis so that it can carry very high bending stress. So these are what we have learned in our solid mechanics or strength of materials course during our first year of engineering, right? So we use a similar approach here also. I quickly go to some of the basics of mechanics, which is helpful in understanding the mechanics of composites. So we have stress. What is the stress? Is nothing but it is the resistance of the body against any load. So it is the internal force which is developed in the body. So when I take this, which is applied with so many arbitrary loads, and I cut a section, and in the bottom figure I have shown the free body diagram. Delta Pn is the normal force. Delta Ps is the shear force of the body on the body. Delta P is a resultant force of all the considering all the arbitrary forces which we have applied here. So when I take that delta P by delta A will give me the resultant stress in the direction of the delta P. Delta Pn is the normal stress. When I take delta Pn by delta A and limit the area of this delta A to 0, then I get sigma n about some point at that point. So at any point I get one normal stress sigma n and one shear stress tau s, right? So this is just shear stress. Now there may be different components of shear stress which we'll learn now. Now, for example, if I have shown in this figure, I have sigma x, tau xy, tau xz. So at any particular point, I have 6 components of stress. In that, 3 are normal, sigma x, sigma y, sigma z, and 3 are shear stress, tau xy, tau xz, and tau zy. And the nomenclature of this is simple. Sigma xx is nothing but the stress acting on a plane with normal along the x direction, and the direction of the stress is also along the x direction. The first subscript says the direction of the normal, the second subscript says the direction of the stress. Similarly, I can take tau xy. In that tau xy, the first index x means the plane on which tau xy is acting has a positive x direction as the normal to the plane. And y is the direction of the shear stress or the stress. It is acting along the y direction. So this is our notations for the stress, right? Sigma x and tau xy. Similarly, I can also give some names to tau xz, tau zy, and tau zx. And by considering the rotational moment equilibrium, I can also consider that tau zx is equal to tau xz and zy is equal to yz. And there are 9 components of stress in the tensor, but can be made it as 6 components of independent stresses due to the symmetry. Right. Similarly, I can also deal with the strain. Strain is nothing but it is the change in length to the original length is what we call it as a strain. Strain along x direction is nothing but it is del u by del x. U is the displacement along x direction. So we can write down epsilon x, epsilon y, and other shear strain also in terms of the displacement components and by taking the partial derivative with respect to x and y and z. Okay, so gamma xy is the shear strain. So which is nothing but is equal to the shear strain is nothing but it is a change in the angle, right? The earlier DA and AB are perpendicular to each other in this figure. Now, due to deformation, D dash, A dash, and D dash, A dash, B dash, they are not perpendicular. The change in this 90 degree is nothing but theta 1 plus theta 2. That is nothing but our shear strain. What is the change in the angle happening because of the shear forces, because of the loading, general case of loading we have applied? That gives us what is known as the strain, shear strain. It is written as del v by del x plus del u by del y. And similarly, I can also write other components of strain. So there are 6 components of stress, 6 components of strain in this particular problem. And we also have 3 components of displacements, u, v, and w. So therefore, in an elasticity problem, we have 3 displacements, 3 stresses, and 3 strains. 15 number of unknowns are there, and we have to solve for these 15 unknowns. So this is the basic background of the elasticity. Now let's come to the composite material and how we can use these types here. We need constitutive equation. What is a constitutive equation? It's nothing but we have to characterize the individual material and the reaction to applied loads. That's what we call it as constitutive equation. For example, you take the Hooke's law, which connects the stress and strain, also is known as a constitutive equation. So there are different types of materials we have, which is homogeneous material. The material properties are same throughout the body. The matter is same throughout the body. That's what we call it as a homogeneous material. Heterogeneous, if they are not same, we call it as heterogeneous material. Isotropic material, every material property in all direction at a point are same. If they are different, we call it as anisotropic material. What is the difference between isotropic and anisotropic when you apply the load? For example, if I take an isotropic material and apply the normal stress, you look at the figure. So we are applying the normal stress along the longitudinal direction or the transverse direction. What happens is that the one along the direction of the load, the material will elongate, and transverse to that, it will shrink. So there is no shear when you just apply the uniaxial stress here. But whereas if you take orthotropic material, when you apply the in-plane load, it will undergo shear. And similarly, when I apply the pure shear for an isotropic material, what happens is it just undergoes shear. No normal strain when you apply the shear strain. The shear and the axial strains or stresses are not coupled. In case of anisotropic material, you can see in the bottom figure, when you apply longitudinal or the axial stress, it will undergo some kind of shear also. And when you apply the pure shear stress, it will undergo shear. In addition to that, there will be normal strains also, or normal stresses also generated. So that means the normal axial and the shear stresses are combined in case of coupled in case of anisotropic material, and in case of isotropic material, they are not coupled. So that's the only difference between the isotropic and orthotropic material. The next complicating effect is coming with the elasticity. Let's come to the generalized Hooke's law. So these are the things you have already learned in your elasticity or in solid mechanics. I'm just going through it quickly. In an isotropic material, this is the generalized Hooke's law when it is subjected to sigma x, sigma y, sigma z, tau yz, tau zx. There is no coupling between the normal stress and the shear stress here. This is one good thing about the isotropic materials, they are not coupled. And we only require two independent material constants, E and the Poisson's ratio, Young's modulus and the Poisson's ratio. G can also be written in terms of E and Poisson's ratio. Therefore, we only require two material constants. Okay, now let's come to generalized thing. What problem we have, let's consider that. When you consider generalized Hooke's law, sigma ij, as I said, it's a second order tensor, and epsilon kl, epsilon is the strain. Strain tensor is also a second order strain. So it includes 9 terms in which it's a 3x3 kind of matrix in which you have 6 independent components due to the symmetry. Sigma ij also has got 9 terms, out of which 6 are independent components. To connect these two second rank tensor, we have a fourth rank tensor which is known as the stiffness tensor. It's the fourth order or the fourth rank tensor. Similarly, I can write it in other way in terms of epsilon, in terms of sigma, I call it as a compliance matrix or compliance tensor. So they have IJKL are varied between 1 to 3. Therefore, I have the number of terms I have in this C matrix or the C tensor is 81. It is 3 to the power 4. Right? There are 4 index. Every index will vary for 3. So it is 3 to the power 4, 81 terms. But all are not independent. So the number of independent terms are lesser. So we don't have to worry about how to get these 81 terms. Sigma ij and epsilon ij are symmetric, which we have already said due to the moment balancing. So I can say sigma ij is equal to sigma ji. Now I can only have 6 into 6, 36 terms. Independent. We don't know how many terms are required finally, but that reduces our job in a significant way. Okay, so how we can further reduce or how it is reduced, let us see. Now let us see, I have a constitutive relation. Sigma is connected to epsilon with this constitutive, or this is the stiffness term. Stiffness matrix is called as C. Sigma is equal to C into epsilon. We call it sigma 1, sigma 2, sigma 3 are nothing but sigma x, sigma y, sigma z. Instead of writing in xyz coordinate, we are writing in terms of 1, 2, 3. Just for the sake of making it generalized to write in terms of the index notation, we are changing that order. Right. So when I want to write down the strain energy in the body per unit volume, I just will write that it is half into stress into strain. It is per unit volume. If you want to integrate it for the whole volume, you can integrate it. Right. So this is W. I just substituted for sigma here in terms of Cij epsilon j. So this is our strain energy in the body per unit volume of the body. What I do is I just take dW by d epsilon I and dW by d epsilon j. So that it's a partial derivative, I can get only Cij. This derivation, if I take this differentiation as a partial derivative which I have taken, it doesn't depend on whether if I take the derivative with respect to epsilon j first or epsilon I first. It should be same. So therefore, dW by epsilon j, dW by epsilon I is also equal to Cji. Therefore, I can say that Cij should be equal to Cji. So therefore, they are also symmetric. Cij and Cji are symmetric. Thus, we only have 21 independent parameters in the general stiffness matrix. SoCijlk becomes Ijkl for symmetry of strain. Then we have symmetry of stresses, and from the energy consideration, strain energy consideration, from 36 to 21 is obtained. This should be 50. This should be 56. There is a typo. I will correct it and send it to you. Okay, so we have reduced from 81 to 21 constants for the in the constitutive equation. Okay, so now let us see, this is that equation. Sigma 1, sigma 2, sigma 3, sigma tau 2, 3, 3, 1 and 1, 2 is connected by this stiffness term. Right? So therefore, I can now also invert this and write in terms of the compliance matrix as given in the inverse relationship. That is, strains are written in terms of the stress using the compliance coefficients. So we have 6 by 6, 36 terms, but we don't need all 36 terms. It is symmetric. So therefore, I require 6 plus 5 plus 4 plus 3 plus 2 plus 1. 21 terms are enough. Right. So therefore, 21 independent parameters are required for any general material. Now we use this material symmetry in order to reduce this number further. So any doubt you have, you can stop me and you can ask the question. Any doubt till now from anybody? Okay, fine. Yeah. Okay, no problem. So now we need to do a lot of simplification. In the simplification, what we do is we consider, for example, if we consider that this block is symmetric about 1, 2 plane. So we have considered two different coordinate system, 1, 2, 3 and 1 prime, 2 prime, 3 prime. And we have assumed that this is symmetric about 1, 2 plane, right? So in that case, what happens is sigma dash 2, 3 will be equal to minus sigma 2, 3. That is because we have changed the direction of the normal. It is a kind of reflection. When you consider the reflection, this 2, 3, 3, 1 and these terms will just change the sign. Sigma dash 2, 3 is equal to minus sigma 2, 3. That is the definition of the shear stress will also change because of the change in the normal. That's what we have done. So it is minus sigma 2, 3, sigma dash 3, 1 is equal to minus sigma 3, 1. And similarly, the strains also will change. So therefore, our sigma 2, 3 is sigma 4. Sigma 4 dash is equal to minus sigma 4. Sigma 5 dash is equal to minus sigma 5. And similarly, the strains. Now, what we can write using the stiffness term, sigma 1 dash is equal to this using the stress strain relationship. and we assume that sigma 1 dash is equal to sigma 1 because 1 and 1 dash are same. Therefore, I can write that epsilon 4 is nothing but minus epsilon 4 dash is nothing but minus epsilon 4. Epsilon 5 dash is nothing but epsilon 5 dash is nothing but minus epsilon 5. That's what we have changed. But if you consider this 1, 2, 3 coordinate system, I can write sigma 1 is equal to this much. These two has to be same at all times. How it is possible then? Because one has got minus and another has got plus. The sum of these two has to be 0. That means C14 epsilon 4 plus C15 epsilon 5 has to be 0. This term has to be 0, then only it is possible. Therefore, I can say that C14 is 0 and C15 is 0. Epsilon 4 and 5 can't be generalized to 0. Therefore, we say that C14 is 0, C15 is 0. Similarly, we can also do it for sigma 2 and we can say that C24 is 0. We can do it for C25 0, C34 0. So there are a lot of terms which are getting to be equal to 0. So now we have reduced from 21 to, we have reduced 8 number of parameters. We just require 13 independent parameters if you have material symmetry like this. Okay. Similarly, if I go monoclinic, one plane of symmetry, so that means monoclinic means the material has got one plane of symmetry, which I showed in the previous slide. The same thing which I showed here. This is called as monoclinic plane of symmetry. So in which what is the significance of this is, if this is the stiffness matrix, I don't have this term. This fourth column and fifth column are 0. You can see 0, 0 is written there. So these corresponds to the transverse shear stress. For example, if I apply sigma 3 to this, the normal stress sigma 3 to this, what will happen is that sigma 23 is connected with C13, C23, C33. These two terms are 0 and you get C36. The physical meaning of this is that it will elongate in the third direction and also it will shrink in the other two perpendicular direction because of the Poisson's effect. And also in addition to that, it has got some in-plane shear which can be shown in the figure. There is in-plane shear, but there is no transverse shears XZ and YZ coming into picture because of the symmetry. So we introduce a lot of symmetry and then it becomes very simple. If you have two orthogonal planes of material property which is symmetric, so you don't get any coupling term between the shear stress and the normal stress. There is no interaction between normal stress and shear stress. Therefore, the number of unknowns which is required is further reduced. So let's count how many do I require. 1, 2, 3, 4, 5, 6, 7, 8, 9. I require 9, not 13, because I have taken the material as orthotropic. What physically orthotropic means is, if you see the figure, it is shown as 1, 2, 3. 1 is the direction of the fiber. So this property of the material, for example, Young's modulus along the E1 is different compared to E2 and E3, right? That is the orthotropy. Our orthotropy is simplification. For example, if I say E2 can be considered same as E3. Both are perpendicular to the longitudinal direction. So that's what we have to say, that two orthogonal planes of symmetry. So E2 and E3 are same. So in that case, we call it as an orthotropic material, right? Similarly, we go for one more simplification, which we call it as transversely isotropic. At every point of material, there is one plane in which the mechanical properties are equal in all directions. For example, if I take the plane DGCF, material property at any particular point, if I choose, the properties are same in any direction on that particular plane. So please remember, we are talking about a particular plane. The material properties remain same in all direction in that plane itself, that plane only. So that's another simplification. We call it as transversely isotropic. So in that case, what happens is these properties are reduced to 5. So now we don't need 13, we don't need 9, we just require 5 constants. 5 constants can be easily obtained from the experiment. So if you make it isotropic, 5 reduces to 2. So from 81 we started with the 3 to the power 4 number of terms. By doing some simplification using our elastic properties, we have reduced it to 5. If you make it isotropic, it can be further reduced to 2 independent constants. So this is the very significant reduction has been done by using the elastic approach. Right. Next, we go to the properties of this. As I said, we require different material properties. I say E1, E2, E3 are the Young's modulus along direction 1, direction 2, direction 3. Okay, so these are the different directions we are talking about. 6 Poisson's ratios, nu1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2. 2 for each plane. So 3 plus 6, 9. And then we have 3 shear modulus. So therefore, we require 3 plus 6 plus 3. 12 number of parameters are required. They are reduced or they are simplified further. Gamma ij, for example, is the Poisson's ratio. What is the definition of this ij? Is the transverse strain in the jth direction to the axial strain in the ith direction. So many of you remember that the Poisson's ratio is nothing but it is a ratio of the transverse strain to the longitudinal strain. So we are measuring in different directions. So therefore, instead of just saying Poisson's ratio, we are saying Poisson's ratio Ij. You measure the strain in the jth direction, and when the load is applied along the ith direction. So this is our definition. This can also be reduced to 3 by taking the reciprocal relationship, where you can say that nu1 2 by E1 is equal to nu2 1 by E2, or in general, Poisson's ratio Ij by Young's modulus I is equal to Poisson's ratio Ji by Poisson's Young's modulus J. This is a very simple expression which reduces 6 Poisson's ratios to 3 Poisson's ratios. Even when you take transversely isotropic or in the orthotropic case, this 3 reduces to 2 because one is that we have 2 planes of symmetry, therefore 2, 3 and 1, 3 can be made same. With respect to the figure which I showed in the previous slide, I am talking about that. How do we derive this? Let's see how do we get this equation. So I said about the reciprocal relationship. In the reciprocal relation, what we do is that we first, there are 2 figures here. In the first figure, in the left side figure I'm talking about now, we are applying the load along the x1 direction. X1 direction, I'm applying the stress sigma. This has got A by A is the dimension of this. So in that, what is happening is when it is subjected to longitudinal stress along x1 direction, u1 because of 1, u1 of 1 is the displacement along x1 direction when the load is applied at the x1 direction, one direction. u2 because of 1 is nothing but displacement along x2 direction when I apply the load along x1 direction. So this is the just simplification or the terminology we use for writing down what is the displacement. So now what happens? I get 2 components of strain. I get 2 components of strain. Epsilon 1 because of 1 is nothing but I am getting the longitudinal strain when I have applied the strain or when I am measuring that along the one direction, which is nothing but sigma by E1. Sigma is the applied stress, E1 is the Young's modulus along the direction 1. The transfer strain epsilon 2 because of load applied at 1 is nothing but Poisson's ratio times sigma by E1. Poisson's ratio is nu1 2. I am measuring along it is the same definition which I showed earlier, measured at 2 when the load is applied at 1, sigma ij, or the Poisson's ratio ij. So sigma by E1 is nothing but epsilon 1. So what is epsilon 2 is nothing but minus Poisson's ratio 1 divided by R into epsilon 1. So this is a general definition of Poisson's ratio. We are still using it. Similarly, I change the situation where I have gone. In the next case, what we are doing is we have applied the stress along two direction, x2 direction, and u2 of 2 becomes the longitudinal in that direction, right? So therefore, epsilon 2 because of 2 is nothing but sigma by E2. Sigma is now applied along x2 direction. Therefore, epsilon 1 because the load is applied along x2 direction, we have to use the Poisson's ratio 2:1. Poisson's ratio 2:1 because we are measuring the strain along direction 1 when the load is applied along 2. So this is what we are doing here. Now let's come for the displacements. U1 because of 1, this is the x1 direction load, is nothing but A into sigma by E1. Length into strain will give you the displacement, right? So therefore length A of the block or the element we have considered, length into sigma by E1. Sigma by E1 is nothing but the strain. The strain into length, which we get the displacement. Similarly, U2 because of 1, because of the load at direction 1 is nothing but minus epsilon 22 into A. Minus epsilon 22 into A gives us the displacement along the x2 direction when we applied the load along the x1 direction. Similarly, U1 because of loading along x2 is nothing but minus A into Poisson's ratio 2:1 by E2 into sigma. And similarly, U2 because of x2 loading is nothing but A into epsilon 22 because of 2. So these are the definitions of the displacement. So therefore, we have written all the displacements. Now there is one relation which is called as Betti's reciprocal relationship. So this we have learned in our elasticity or in our mechanics course, where we solid mechanics course, where we say that because the material geometry is same, U2 because of 1 is also equal to U1 because of 2, because we have applied the same sigma everywhere, right? So displacement U2 because of load applied along one direction is also equal to the displacement along x1 direction when the load is applied along x2 direction. So this is a reciprocal relationship. If I use this relation, I can easily say that the Poisson's ratio 1:2 by E1 is equal to Poisson's ratio 2:1 by E2. This actually reduces our calculation. We don't require 6 number of Poisson's ratio. We only require 3, right? So therefore, we have reduced the number of independent terms required from 9 to 5, right? So now we require only 5 components. Similarly, I can also go for the compliance matrix, which is nothing but it is the inverse of the stiffness matrix. Here also we write them in terms of E1, E2, E3, G23, G13, G12, and 3 Poisson's ratio. It looks like 9. When you consider orthotropic or transversely isotropic, we can say that E2 is equal to E3 and G13 is equal to G23 and nu13 is equal to nu23. So we only require 5 number of terms, not 9 also. Right? We can also write these here. Okay, now let us go to the plane stress condition. Why we are using plane stress condition is because that the lamina is like a plane, and the plate, if it is thin, there are no out of plane loads. Sigma 3 direction, you don't have any load. It can be considered as a plane stress condition. And the loads are applied along the direction of along the longitudinal direction of the fiber or along the transverse direction of the fiber. Therefore, we consider it as a plane stress condition. So therefore, we can ignore this gamma 2-3 shear strain. Transverse shear strains can be ignored. The state of stress is just defined by sigma 1, sigma 2, and tau 1, 2. Epsilon 3 is not 0, but it can be ignored by considering S13 sigma 1 plus S23 sigma 2. Right? So we have only 6 by 6 terms are reduced to 3 by 3. The size of the problem is reduced. So that's why we go for the plane stress condition or plane strain condition. So we can now work with in the in-plane condition, we have only 3 by 3 condition. When you consider the transverse stresses in using some, let's say, shear deformation plate theory or the beam theory, you have to consider the transverse shear stress also. But still we make use of the plane stress condition. And in addition to that, we have transverse shear stress also, so that the problem is much simplified further. Okay. One more thing we have to learn in the mechanics is the coordinate transformation. Why do we need to do the coordinate transformation? Now, in this, I have shown sigma p and sigma m. So, sigma p is nothing but it is with respect to the problem coordinates, xyz coordinate. Now, imagine that you have four number of layers, lamina. In four number of lamina, you have one lamina with 0 degree fibers, another with 45 degree fibers, let's say third with 90 degree fiber, another maybe with 60 degree fiber. So 60 degree, 30 degree, 90 degree, all are measured with respect to our global XYZ coordinate system. But when we are writing the properties of the lamina, we are writing it with respect to the direction of the fibers, right? So with respect to that local coordinate system, that means we have two types of coordinate system. One is with respect to XYZ, another with respect to the material coordinates, that means very local coordinate system, which is x1, x2, x3. So sigma p corresponds to the problem coordinates, that is the global coordinates of xyz, and sigma m nothing but it is the material coordinates, which we call it as x1, x2, x3. Now we are dealing with sigma xx, yy, zz, 1, 1, 2, 2, 3, 3. So our problem is actually increasing, and the sigma m and sigma p, the material and the problem coordinates are connected by the direction cosines. Lij are direction cosines, which is nothing but the dot product of two normals we can write. So dot products are usually written in terms of cos theta, and the magnitude of these unit vectors are 1. Therefore, they just give the cosine angle between the two normals, right? So that this is actually what we have learned in the vector algebra also, right? So therefore, what I can do is, if I know the problem coordinate stresses, I can transform that to the material level, or I can do it vice versa. If I know the stresses in the material coordinate system, I can get the problem or the global coordinate system stresses by doing the coordinate transformation. So where L is nothing but it is a 3 by 3 direction cosine matrix, Lij. I just change Ij 1, 2, 3, 1, 2, 3. So I can just get the 9 terms of the Lij. Right. So this is nothing but the direction cosines, which can be obtained as the cosine angle between the two unit normals. Okay, so this is just a general sense. How do we do this actually? It's very simple. So I'll go with the. So you may be remembering what you have done in case of strength of materials, right? When you were doing the stress transformation, strain transformation, we use the same principle here. So the way we have written in the previous slide can be very easily simplified into a very basic equation. Many of you remember that when you have xyz coordinate system, plane stress xy stresses are known, and you are asked to calculate what is the stress, normal stress along the x dash line, or sigma y dash, or sigma x tau x dash y dash. You did it very easily in your strength of materials. You plotted Mohr circle, you calculated the principal stresses, principal planes, you did Mohr circle, everything you did already. So we use the same approach here also. So sigma x dash is nothing but these equations are familiar to you. I'm not repeating this equation. Sigma x plus sigma y by 2 plus. When you know sigma x, sigma y, and all the tau xy, I can easily get what is the stress at a plane which is at theta from the x direction. Or this can easily be done. Right. Similarly, the strains can also be obtained applying the transformation of the plane strain also. This also you have done in your strength of materials or solid mechanics courses. So this is the strain transformation equation, and in the previous slide I have shown the stress transformation equation. Right, I can combine this and say that, let's say sigma 1, sigma 2, tau 1, 2, I can now easily say that 1, 2 is nothing but they are the problem coordinates. XY is nothing but they are corresponding to the problem coordinates. 1, 2 is the material coordinate system. C means cos theta, S means sin theta, right? So when I say transformation, I'm just saying sigma 1 can be obtained with the help of sigma x, sigma y, tau xy. I've just written the same equation in terms of a matrix. So T is nothing but a transformation equation, transformation matrix, which is including cos square, sin square theta, cos theta, sin theta, and those things. I can do the inverse also. If I know sigma 1, sigma 2, tau 1, 2, I can also obtain sigma x, sigma y, tau xy using the inverse approach, right? So if I know sigma 1, sigma 2, tau 1, 2, I can calculate the global stresses also, right? Similarly, this is the strain transformation. So if I know the global strain terms, I can get for the material direction what are the strains, the normal and the shear strains, using the theta, cos theta and sin theta. Fine. So this is the transformation, strain transformation. But only one problem is that if you remember, when you plotted the Mohr circle for the plane strain condition, the maximum shear strain you get was gamma max by 2, not gamma max. Whereas for the stress transformation, when you plotted the Mohr circle, it was tau max you obtained. The maximum shear stress was equal to the radius of the Mohr circle, and the maximum shear strain by 2 is nothing but the radius of the. So there is one term which includes half gamma by 2. So this is the due to the transformation we have obtained this, and we have to retain this 1 by 2 term. So that we are doing also. What we are doing in the coordinate transformation is we are just retaining that 1 by 2 term here. So we are writing 1 by 1 by 2, and we are just writing it in terms of we have to use the same transformation equation in order to solve this problem. By doing all this, what we can get is that the stress and strain are connected. So this is what we want to say. The stress and strain are connected in terms of this. S is nothing but it is the compliance matrix, and it can also be written in terms of C matrix. R is nothing but this 1/1/2 this matrix, and T is the transformation matrix. So we do this transformation, we can change from the material to the problem coordinate system or vice versa. So we have to do that because each fiber will be having in different direction. Their longitudinal properties may be different, their transverse properties may be different when you go for the global coordinate system. Therefore, it is the first job to do is to do the coordinate transformation. Without doing this transformation, it's not possible to do the one global set of equations is not possible to derive. So therefore, it is essential to do the transformation. So how it looks, the transformed compliance matrix looks like this. We denote it by S bar. S is the compliance matrix. We have done the transformation from local to global. So therefore, S11 bar, 12 bar, 16 bar. So these bar terms are nothing but they are the transformed compliance matrix. So they can be written in terms of cos theta, sin theta terms, which are shown in all this equation, S11 bar, S12 bar, and so on. Similarly, I can also get the reduced stiffness. We call it as transformed stiffness, and also we call it as reduced because we have reduced from 6 by 6 to 3 by 3 and implemented the plane stress condition into this. So therefore, it's called as reduced stiffness, which is transformed. So therefore, we call it as transformed reduced stiffness matrix, right? So this is one thing. Okay, so this is the general equation, which includes mechanical as well as thermal terms. Now, if you look at the first equation, sigma 1, sigma 2, sigma 6 for any kth layer is nothing but this is the stiffness matrix, the reduced stiffness matrix into epsilon 1, 2, 6 and minus alpha delta T is also included in this. Alpha delta T is nothing but this is the thermal strain. Alpha is the coefficient of thermal expansion and delta T is the change in the temperature. If there is a change in the temperature because of the thermal property, there is actually one thermal stresses also developed, thermal strains are also developed. and you get the stresses because of that. That can be obtained in this. So this is also nothing new because we have also dealt with the thermal stresses strains also, and you know that they are always negative to what you have. When it is expanding and you are restricting them, it is actually negative. When it is you are compressing and it is trying to expand, it is also opposite to what the mechanical stresses or the strains are doing it to them. Right. So therefore, we have minus alpha delta T terms also coming into picture. We don't have any shear change because of the change in the temperature. Therefore, we don't include that. In some cases, yes, we do get 1, 2 also, but they are not that significant. Right now, we only consider that alpha 1, alpha 2 are the only two coefficients of thermal expansion along the longitudinal and transverse direction. Right. So, and this is sigma 4, sigma 5 are nothing but they are the shear terms. Okay, so these are the general expression for this. And similarly, I can also write down the same thing I have written in terms of cos to the power 4 theta. In the previous equation, it was written C4 S4. We are writing it in a general sense. This is also same as what we have done before. Now I go with for the micromechanics approach. Whatever we have done till now is part of the macro mechanics. First, we started with macro mechanics. We assume that we know the properties E1, E2, E3, G12, and all the properties we know. We assume that we know that. Then we went for the global property and the stiffness, the constitutive equation, and so many things. But we don't know how to get even the Young's modulus in the longitudinal direction of the fiber or the composite. We don't know how to get it. That's what we have to do it now. That's what we call it as micromechanics of the composite. We are only dealing here with the stiffness terms. What we do is fiber packing is arbitrary. We use average of stresses and strains. There are a lot of approaches to do this micromechanics. One is to get the actual by using some multi-scale modeling and kind of thing to get the properties. Then you can go for the closed form solutions or go for the numerical solutions like finite element modeling along the thickness direction, so that in the fiber microscopic level you can do the multi-scale modeling and then you get the properties. It's just getting the characteristics of the composite material. Are some variational methods you can use to get this. What we are going to do here is we follow the strength of materials approach. It's very basic approach we follow here to get the properties of the composite when you know the properties of the fiber and property of the matrix. So for that we require some of the definitions. Volume fractions. Volume fraction Vf is nothing but volume. It is just the ratio of volume of the fiber to volume of the total composite. Vf by Vc. That is a volume fraction of the fiber. Volume fraction of the matrix is nothing but volume fraction of the matrix or volume of the matrix divided by volume of the composite. So how many percentage of matrix you have in the composite? That is nothing but the volume fraction. How many percentage of fiber is there in a particular composite? That is a volume fraction of the fiber. So if you have void, how many percentage is void in the volume? So that is the volume fraction of the void. So if I add all the percentages, I should get 1 or 100%, right? So therefore, volume fraction of fiber plus matrix plus void should be equal to 1. And if you add all this, you should get the volumes. If it is added, you should get the volume of the composite completely, right? So these are some of the definitions we are doing for the volume. We can also do it for the weight also, using the weight fraction also you can do. So what percentage of fiber in terms of weight is part of the composite? Wf, small wf is nothing but weight of the fiber divided by weight of the total composite. So that is the percentage of weight of the fiber. Similarly, percentage weight of the matrix in the composite. So therefore, voids doesn't have any weight, so we can neglect the voids weight. So therefore, the total composite weight is nothing but the weight of the fiber plus weight of the matrix. And if you say that the density is equal to W by V, you can substitute that WC is equal to WF plus WM. And substituting, I can say that rho C, this density of the composite is equal to rho F VF plus rho M VM. So this is what we call it as rule of mixture for the density. So I hope this is clearly understandable. We just use the simple approach. We have averaged out what is the weight of the composite in terms of the weight of fiber plus weight of matrix, and substituted the density in terms of weight and volume to get the density of the composite is nothing but in terms of if you know the density of the fiber, you know the density of the matrix, you can easily get what is the density of the composite. Because we cannot get what is the density of the composite unless we know the density of fiber and density of the matrix. So this is how it works in a very simple rule of mixture. There are many other micromechanics approach. If you go for any uh, textbooks on mechanics, you can find a lot of micromechanical approaches are available. Okay, so you can follow that later. Yeah. Now I'll go one by one how to get the modulus of different material. So what we are assuming here is we know the Young's modulus of the fiber, we know the Young's modulus of the matrix. What is our job? Our job is to get the Young's modulus of the total composite in the longitudinal direction. So for that, what we are doing is we are applying, if you look at the figure, EF, EM are the Young's modulus of the fiber and matrix. AF, AM are the length or the depth of the or the thickness of the block for the fiber and for the matrix. I have applied a force P, which is the longitudinal direction. So what we are assuming is that the strain of the fiber and strain of the matrix are same as the strain of the composite. Epsilon F and epsilon M is same as epsilon C because the loading direction and the boundary condition is such that you can assume that. The stresses are not same because the properties of each material are different. If you say that the stress is nothing to do with the material property, yes, you are right. But the problem is that when you write the stress in terms of the Young's modulus and the strain, if you consider the strain, it's depending on the material property because the strain also will alter. In general, you say that the stress is nothing but load by the area on which it is acting. It doesn't depend on material property, right? But when you look at the strains and then you go from the strains, it has to be depending on the material property. So therefore, what I am doing is P, that is the load applied here, is nothing but the load carried by the fiber plus the load carried by the matrix. This is the equilibrium equation. The total load P is nothing but the load carried by the fiber. Sigma into AFB is nothing but the area of the fiber, and AMB is nothing but area of the matrix. Therefore, the sigma C is nothing but P by AFB plus AMB. So now what we can do is AFB is the area of the fiber, AMB is the area of the matrix. This area of the fiber divided by the total area of the composite, then also you get the volume fraction of the fiber in terms of the area, right? So you can do it with respect to the volume, you can do it with respect to the weight, you can do it with respect to the area. So therefore, if you use the definition in epsilon E11 is nothing but the Young's modulus along the longitudinal direction of the fiber is nothing but sigma C by epsilon C. You get the Young's modulus of the composite in the longitudinal direction is nothing but VF EF plus VM EM. This is also a simple rule of mixture to get the longitudinal modulus. Okay, I hope this is clear. Next, we go for the transverse modulus. What is the transverse direction Young's modulus? E2, for example. E2 of the composite, when you know the Young's modulus of the fiber, when you know the Young's modulus of the matrix. Here, what we assume is that the strains are not same because you are applying the load in the transverse direction. Young's modulus of the fiber is given, Young's modulus of the matrix is given, and you know the thickness of these blocks, right? So, and the stresses are same because you are applying it in perpendicular to the plane, right? So the stress in the fiber is equal to stress in the matrix and is equal to the stress in the composite. So when we use this assumption and we are writing it, what we are writing here is epsilon C into this length is nothing but what is the displacement of the composite because of the load is nothing but the displacement of the fiber plus the displacement of the matrix. Displacement of the fiber and displacement of the matrix. Therefore, I can simplify this and get some kind of equation which is equal to Young's modulus of the composite in the transverse direction is equal to 1 by Vf by Ef plus 1 Vm by Em. So in general, if you have more than one fiber, you have more than one matrix, then also you can just keep on adding this. You have fiber 1, you have fiber 2, you have matrix 1, you have matrix 2. Then also it can be, the relation is same. You have to just keep on adding different fibers, different matrices in this expression and also in any other expression, right? So this is the effective transverse modulus. So similarly, we can get the shear modulus. In the shear modulus, what we assume is that the shear stress in the fiber and the shear stress in the matrix are same as the shear stress in the composite. So when you do that, epsilon, if the shear stress are same, the strains has to be discontinuous. Epsilon 1 to F is not equal to epsilon 1 to matrix. The shear strain of the composite is nothing but, this is the expression which is shown in just below the figure, epsilon 1 to C into AF plus AM. That is the displacement or this is the shear strain into the length is nothing but the change in the angle. Is nothing but the change in the angle of the fiber plus for the matrix. Therefore, I can say this expression gives us what is the shear strain of the composite in terms of the shear strain of the fiber and shear strain of the matrix. So combining these, I can get what is the effective in-plane shear modulus of the material using the expression which is shown is GC is equal to 1 by Vf by Gf plus Vm by Gm. Same, if you have more than one fiber, you can just keep on adding them, or you can just have more than one types of matrix, you can also use them. It's also possible. And the last one I have is for the getting the Poisson's ratio. To get the Poisson's ratio, what I need to do is I have to get the two strains, one along the 2-2 direction, one another along the 1-1 direction. The definition of Poisson's ratio 1-2 is nothing but the transverse strain epsilon 2 divided by epsilon 1-1. Let the transverse strain to the longitudinal strain. And here we are saying that the longitudinal strain epsilon 1-1 for the fiber is also same as epsilon 1-1 for the matrix, which is also same for the composite. Epsilon 2-2 can be written in terms of the epsilon 1-1 using the Poisson's ratio. So that's what our basic definition of the Poisson's ratio is, right? So therefore, epsilon 1-1, 2-2 of the fiber and matrix, if they are known, I can now say that epsilon 2-2 of the composite is nothing but delta U2. Delta U2 is nothing but the change in the length divided by the total length, right? Therefore, change in the U2 is nothing but the displacement change in the length of along the x2 direction divided by the total length, that is the AF plus AM. Total length means in this case it is total thickness. Therefore, I can easily write that E epsilon 2 to F AF plus epsilon 2 to M AM by the total area of the composite in the 2 to x2 direction. Therefore, I can simplify this and say that Poisson's ratio 1-2 for the composite. If you know the Poisson's ratio 1-2 of the fiber and 1-2 of the matrix, then easily the rule of mixture can be used in order to obtain the Poisson's ratio, the effective Poisson's ratio, or in general, any effective material property can be obtained using the micromechanics approach. When you use the volume fractions of the fiber, volume fractions of the material matrix, and you know the bulk properties of the fiber and properties of the matrix. So this is what we can do using the micromechanics approach. This is very simple approach which I explained here. There are many complicated or many involved methods are also available, like Mori-Tanaka method, Shelby method. So many methods are available, so one can go through those methods. So with this, I have completed my lecture. So these are some of the references which I have used, and if you find they are interested, you can go through these references. And thank you for your patient listening.
Thank you, sir, for the wonderful lecture. Hello.
Yeah.
So now I am having some few questions from the participant side. Why
Yeah,
does
please.
lattice stress generate in the formation of composite material and how it affects on the lattice strength?
Sorry, I didn't get your
Why,
question.
why does lattice stress generate in the formation of composite material and how it affects on the lattice strength?
Lateral stresses are why are the lateral stresses developed?
Yes, sir. And how it will affect on the lattice strength?
Okay. So for orthotropic, if I am understanding your question correctly, you are asking about how am I getting the lateral, this correspond to this slide, right?
Yes, sir.
Okay. So if you look at this equation, this is for the isotropic equation. I'm coming to this. So if I, for example, I'm looking at the inverse relation here. Inverse relation here. So what happens is when I apply sigma 1 here, right? Apply only sigma 1 here. Let's say all other things are 0, right? So I get epsilon 1 is equal to S11 into sigma 1. Epsilon 2 is equal to something into sigma 2, sigma 1. Epsilon 3 also can be written in terms of sigma 1. Epsilon 4, epsilon 4, 5 are all in terms of sigma 1. So if I only apply the sigma 1, I can get both normal as well as shear strains for only applying sigma 1. This is just a mathematical expression. Okay, next, if I come for uh, this one, why do I get shear when I apply the normal stress? Is that your question correct?
Yes, sir.
Okay, so that is because in case of homogeneous material, the elastic properties are same in all the directions. That's what we said, right? But in case of anisotropic material, the 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 properties are different. That means the strength of one, for example, if I take a material in one particular direction, it may be very strong. In another direction, it may not be that strong. So when what happens if you apply in any general direction, in its strength is not uniformly distributed, or its properties are not uniformly distributed in different directions, so therefore it undergoes normal as well as shear strengths both. So because of its non-uniformity of the distribution of the properties in all directions, so it behaves like this.
Sir, the next question is what is present trending area of research on composite materials?
Sorry, what is
What is present trending area of research on composite materials?
present means
Trending area. They are asking about the applications or the trending area of the research on composite materials.
you mean what is the
Recent
latest
area. Present recent area of the research on
yeah,
composite
yeah.
materials.
What is the latest research area, right?
Yes, sir.
Okay. Latest area means people are now using damage mechanics into this to know what is the defects, what kind of delaminations are doing, what is the damages are doing in the thing, and how the waves propagate in these type of structures, how the defects or damages can affect those things, how to get the extent of damages acting in this, what is the behavior of thermal, mechanical, piezoelectric effect affecting the global behavior of the composite materials. There are a lot of things going on. Even people are working on different micromechanical approaches, different modeling techniques for the modeling the fiber. What happens, for example, if a fiber breaks within the composite material? How much the strength and how much the stiffness of the uh, overall composite has degraded. So if a particular fiber is broken, if a particular matrix is broken, it's just a damage mechanics. It is just fracture. Also, there are a lot of areas going on. Even the fibers, whatever we have shown here, they are linear fibers. Even we are also using the variable stiffness fibers, where you can keep the, or you can place the curvilinear fibers, parabolic fibers, where the angle is changing at any xy location, so that you can you can grade it further. Not only the direction of the lamina, number of lamina, you can also in a plane you can vary the dimension, you can vary the orientation, you can do so many things.
So their next question is, can we apply reciprocal relation to the sandwich beam?
Yes, you can do that. You can do the same thing for a sandwich also. And the only thing is, in the sandwich, the you assume that the you have one very strong material and another is very soft material kind of thing. In that case, yes, you can use the same relationship, but your beam theory or your plate theory should be capable of handling the soft, because it has got a lot of shear deformation into that. If you consider that the same mechanical approach which I showed here can easily be useful, but you have to be very careful on the beam or plate mount.
And so their next question is, how to evaluate Hessian damage properties for any composite material without doing experiments?
How to?
Doing experimental analysis.
No, you want to do the experimental analysis and get the
Basically, they
property.
are asking how to evaluate Hessian damage properties for any composite material without any experiment.
Without doing experiment, you want to get out the extent of damage and all, right? So one thing is possible. Now, for example, you want to assess whether there is a damage or not. What you can do is, if you know the what happens when there is a damage is its frequency characteristics change, right? So you know the natural frequency of the pristine structure without damage, and you can compare the same with the damaged structure. So you have, let's say, I have some 5% of damage in the structure, and my natural frequency also will be different, because the stiffness of the structure is degraded, because you know that the natural frequency is nothing but it is the ratio square root of k by m. If the stiffness is reduced and mass is degraded because of the damage, your natural frequency will reduce, right? So you can just say that based on the frequency analysis, just you take a frequency and you can say that there is some damage. But to what extent you need some experimental skill, or you have to go for some health monitoring techniques.
There another question is, in the case of the vibration analysis using the higher order shear deformation theory, how to determine the mass matrix?
How to determine the mass matrix?
For the case of the higher order shear deformation theory for the vibration analysis.
Mass matrix, for that you can do it. Just you take the how do you get the mass matrix? You get it from the kinetic energy, right? So when you have the kinetic energy, and then you go for the kinetic energy, and then you substitute for the velocity terms, because you have kinetic energy, it's nothing but uh, you need mass and you need the velocity, right? In the velocity, you write in terms of all the displacement time derivatives, and then you derive it using the higher order shear deformation theory. It's quite simple.
And they are also requesting for the PPT.
Yeah, sure. I will send the PDF file to your ID. Or if the size is too big, I'll share the link to that. You can, anyone interested can download it.
Okay, thank you, sir. There is one more question: how isotropic and anisotropic material are affected in composites?
How isotropic and anisotropic
Isotropic
materials
materials
are?
are affected in composites.
Sorry, how
Yeah,
isotropic and anisotropic materials are?
affected in composites. Not relevant question.
They are used, or what? What's your question? Can you type it, because I can't hear you properly? How isotropic and anisotropic materials
Basically,
are?
I think a participant wants to ask the difference between the isotropic and anisotropic material.
Okay, that's there in my slide. This slide, which is shown here. In isotropic material, every properties like Young's modulus, for example, you consider the Young's modulus, shear modulus, they are same in any direction, right? That is the isotropic material. Isotropic material, Young's modulus, you rotate the normal or the direction any, you take direction x, you direction y, you take direction z at one particular point. The elastic property or the Young's modulus, shear modulus, Poisson's issue, they are same. The strength is same in all the directions. But when you go for anisotropic material, the Young's modulus may be higher in one particular direction compared to any other direction. They are not equal in all the directions. So that is the difference between isotropic and anisotropic material.
There is one more question, sir. How to define ultimate strength of the laminated composite material?
In the experiment, you have to in the composite, for example, you go for the testing. It's called a scoop and test, where you make a small specimen and keep on applying the uniaxial tension in the using the UTM. You have to go. You have to draw the stress strain curve because it's a brittle failure. You go for till failure and you just get that. It's just a brittle material. It's just a linear curve you get. Or, for example, in some cases, what happens is, if I go back to that slide, I'll go back to that slide. Yeah, here in the left side figure, you can see the topmost stress point will be the ultimate stress point. If you have a composite, you may get the ultimate stress point, which is the highest stress, and then the stress keeps on reducing because of the degradation, and then it breaks finally. It is the way we do for the mild steel. It is same for the composite also.
Thank you so much, sir, for the wonderful presentation or the answering the each questions to the participants.
Okay, thank you.
Thank you.
Thank you so much, sir. Your encyclopedic and explicit knowledge on composite mechanics have certainly developed the foundation of this training program. We now have a 15 minutes break and we will start the third session of the day at 1 p.m. sharp. Thank you, sir, and thank you all.
Thank you, Amriti, and thank you others.
Thank you. Thank you so much. Hello. Good afternoon, sir.
Good afternoon.
Sir, welcome to the Faculty Development Program.
Thank you.
So we
Can you
are
hear me
having
too?
approx 200 registered participants,
Okay.
but they are listening through the YouTube live.
Okay. So they will all log into this particular meeting after 1 o'clock?
Pardon, sir?
All the participants should log into this meeting link at 1 o'clock?
Yeah, definitely they are continuing online through the YouTube live, not through the Google Meet.
Okay. Okay, so this is not like, can we have like, can they ask questions or it is just a,
They can ask questions on the YouTube on the behalf of the participants. At the end of the session, I will ask the questions on the behalf of the participants to the you.
okay. Okay. So YouTube live means, is there a link to the YouTube?
Yes, there is the link. I have created the link and sent it to them, and they are continuing the session through the YouTube live.
Okay.
Good afternoon, everyone. Our third eminent speaker of the morning is Dr. Chandrasekhar Yeramalli. Dr. Chandrasekhar Yeramalli is currently working as an associate professor in the Aerospace Engineering Department at IIT Bombay. Prior to joining IIT Bombay in 2015, Professor Chandra worked in the field of industry for 10 years. He obtained his PhD in aerospace engineering from the University of Michigan at Ann Arbor in US. His research interests are broadly in the areas of environmental damage, modeling of composite materials, fatigue modeling of composites under combined loading, ballistic response of fiber composites with applications to wind turbine blades, and aerospace vehicles and components. He has a plenty of feathers of achievements, some of which include publications in around 40 journals and international conferences, and has 15 patents on his name. Sir, your presence has blessed us all and is indeed going to be really beneficial to us in this training session. I request you, sir, to kindly take us to the journey on micromechanics and nurture the foundations of the same. Over to you, sir.
Thank you very much, Urjasvita, for the introduction. And thank you, Professor Imarti Bhaskar, for giving this opportunity.
Our
So
pleasure, sir.
I let me first figure out how to share the screen so that we will start off. Okay. I'm assuming you can see the screen. Okay. So I'm going to start with this 1 hour lecture is focusing on micromechanics. As you have been going through these lectures, I think since yesterday, if I'm right. So you are already familiar with composite materials and laminate theory and all maybe might have been already covered. We'll take a step back in a sense in the sequence of materials because you're already at a higher order, but we'll go back into the microstructure to understand how to estimate the properties of a composite given the material properties of the constituents, which is more often the case. So micromechanics modeling approach in fiber composites involves the modeling of individual fiber and matrix explicitly. So the interaction between the fiber and matrix is captured through appropriate boundary conditions, and the equations of elasticity are solved in the exact. And also the other big objective is to determine the average properties of the composite by homogenization. So what do we mean by this? So for example, if you see, this is a fiber, okay, and the surrounding blue color is the matrix. So what we have in a typical composite is just shown schematically here in the picture. The fibers or the circles are dispersed in a matrix material, which can be a polymer matrix, or if you are talking about ceramic composites, it can be ceramic matrix. But whatever it is, there is basically a extensive phase, and then there is an inclusion phase. So this is also another terminology. So the inclusion is basically like the fiber, which is inside another material. Now, what we want to do through micromechanics is to homogenize this, because if you think about it, fibers are at a scale of microns, and composite structures are in the scale of meters, or tens of meters. If you talk about wind turbine blades or an aircraft wing. So in that case, we can't continuously take into account the geometry of the fiber. So we want a homogenized set of properties which we can then utilize in our modeling. Now, how do we do this homogenization? Basically, that's what this micromechanics is. That how do we account for the effect of the fiber and the matrix, yet we need not, so that we can then sort of represent this fiber and matrix as a homogeneous material, which I'm showing on the right hand side. And this is the homogeneous material. So what we are showing is a homogeneous material on the right hand side, which has been obtained after the micromechanics formulations or formula have been used to estimate the properties. So we want to represent the body on the left with an equivalent body where there are no more inclusions or anything. It's just a homogeneous material. That is the objective. So there are different approaches to micromechanics. One is the strength of materials approach, which is the simplest, where essentially we model these individual constituents as 1D springs, and we try to estimate the effective properties of these combination of springs. Then the other approach is, the second approach is the elasticity based approach, which is the most accurate, but this approach requires certain assumptions on geometry, and also obviously it's a lot more complicated, and it's restricted to a fewer set of problems. As any of you, if you are familiar with elasticity-based solutions, one would realize that these are the exact. So you are solving the partial differential equations of equilibrium in the exact, which would imply that enforcing boundary conditions or with different geometries, it becomes a challenge. So it has its benefit, but it has its restrictions as well because of the complexity of the solution process. Then the third approach is the finite element based approach. In finite element based approach actually is more, I would say generic. You can apply to wide range of fiber geometries and structures, fiber architectures. But again, it has its challenges in the sense you need to be able to identify a representative volume element, and also these are usually computationally very intensive, because we are talking about capturing a geometry of a structure which is in the orders of microns. So even if you build a millimeter size model, you can imagine how many elements it will end up. So these are some of the other challenges with finite element model. But finite element model is getting more and more used or more popular because its ability to capture different fiber architectures and fiber geometries. So compared to the other two methods. In this micromechanics lectures, I would essentially be giving you I would say, a very small part of the whole micromechanics subject. First is the strength of materials part, which I'll cover, and then I will just cover one solution method for obtaining E11 properties, because I don't think this itself will take up almost an hour's time, and I don't think we'll have time to cover anything more than that. But also another thing I want to say is that micromechanics is a very theoretical subject. If you typically look at micromechanics literature, there is a lot of theoretical solid mechanics based proofs and theorems to validate these micromechanics models. The approach that I'm taking in this lecture is not to really get into the math of why homogenization is right and the various theorems associated with that, but instead try to just give you a solution approach, and so that you are after this 1 hour lecture, hopefully you understand what are the different approaches to solve to obtain the homogenized properties using micromechanics. Okay, so it will not go into the theoretical part of the micromechanics literature. So first approach we will look at is the strength of materials for E11, which is the estimation of fiber direction properties of a composite using strength of materials approach. So before we go ahead, let me just draw. So whenever I talk here in this 1 hour, one is the fiber direction. This is the transverse, and this is the another transverse direction. So one is along the length of the fiber. Okay, so whenever we talk about the composite properties, E11, it would imply that we are talking about the composite properties along the fiber direction. Now, in a strength of material based approach, we model this fiber and matrix as a schematically I have shown here, and we model them as 1D springs. So when you look at that, we can write equilibrium equation for this as a two parallel spring model. So sigma C is the stress in the composite. C indicates composite. AC is the area of the composite. Sigma F is the fiber stress. AF is the fiber area. Sigma M is the matrix stress, and AM is the area of matrix. So M indicates matrix, and F indicates fiber, and C indicates composite in the super subscripts of these formulae. Now, I can then just divide the whole equation by area of composite, and I will get this expression, second expression. Then normally, again, another terminology which I would like to introduce is the this VF term. Normally, VF is defined as the volume fraction, and volume fraction implies a ratio of area of fiber to the area of composite. Okay, so this is ratio, okay, of area of fiber to area of composite. When VF goes to 1, it would imply that the whole composite is made up of only fiber. There is no matrix. And when VF goes to 0, that means there is no fiber present. Everything is matrix. So VF and 1 minus VF are complementary. So matrix is 1 minus VF. The amount of the volume of matrix in a composite is 1 minus VF. So I can rewrite the above equation. Also, what we have done, we have substituted, since we have 1D, we are saying sigma composite is nothing but Young's modulus of the composite EC into epsilon C, which is strain in the composite. Same thing I can substitute for F, sigma F and sigma M, and rewrite this equation as I'm showing here. And then what you can see is that, and also assuming compatibility. So you have a parallel spring model where strain is the same in both the fiber and matrix. Then I can say that EC is equal to EF VF plus EM into 1 minus VF, which is the rule of mixtures. It's a very common rule. You must have used it in many other situations as well. But for composite modulus estimation, this EC is equal to EF VF plus EM into 1 minus VF. This is the strength of material solution for E11. Okay. Now we come to the second modulus, that is the second direction, E22, which is the transverse direction. Now, if you look at the schematic of the picture, one second. Yeah. So if you look at the schematic of the picture, the loading is in the transverse direction. So the fiber is running in the one direction. Now, this is your two direction. So 2 is transverse to the fiber, and we want to find the average properties of this composite material along the 2 direction. Now to do that, what we again do is as I said, it's all simplified assumptions. So we model the matrix and the fiber as a spring. And so now we have a series spring connection. The previous E11 case was a parallel spring connection. In this case, now it's a series spring. You have one matrix layer and one fiber layer, another matrix layer and another fiber layer, like that. And the loading is going to be the same, because whatever load we apply here, okay, this sigma has to be transferred through the matrix fiber, like that. So we can say that sigma is equal to sigma f is equal to sigma m. That means the stress in the stress that we have applied is the same in the fiber and in the matrix layers. Similarly, the displacement that you see in the total displacement of the composite will be the sum of the displacements of the individual matrix layers and the fiber layers, which I have expressed in terms of a summation. Now, we all know that displacement is nothing but epsilon. So delta by L is epsilon in a very generic way. So delta is what? Epsilon into L. So here L is what is the thickness of the layer. And for the composite, it is the thickness of the total composite, which is TC. So I can write delta C as epsilon C times TC. I can write delta M as epsilon M times TM, and delta F as epsilon F times TF. I have taken the TM and TF out of the summation sign because I am assuming the TM and TF are same for all the layers. Okay. And then what we do is we again divide this. We also will express the epsilon in terms of the modulus, because we want to find the effective modulus. So we know that E times epsilon is equal to sigma generically. So sigma by E will give me epsilon. So I substitute that for the composite, for the matrix, and for the fiber. And then finally, we also divide this whole equation by TC, which will give me the T by TC terms, which will give me the volume fraction term. So, which is there on the left-hand side bottom of the screen. So you can see that what I have done finally is divide the whole equation by TC and eliminate the common sigma term. And then I'm left with 1 over EC is equal to 1 minus VF into 1 over EM plus VF into 1 over EF. Now, this gives me the Young's modulus of the composite in the 2 direction. The problem, though, with the 2 direction modulus is that it was found by researchers that the predictions from this model, this transverse modulus of composite E22 model, is not matching that well with the experimental data. And there are many reasons. Some of them might be even obvious to you as you are listening to this. And so we will talk about a few things and how researchers have tried to improve this model. So another model for E22. Now one problem is the load path. As I'm showing in the picture to the right, fiber is there and I'm applying in the transverse direction. The load need not go through the fiber alone, because there is matrix which is continuous around the fiber. So load could be also transferring through that path. Now, the other thing also is, so let's go through those points that I mentioned here. Do not approximate well with exact solutions, as I mentioned. One of the reasons is the simplistic assumption of displacement and load transfer. As the model is loaded in 2 directions, the fiber and matrix would shrink or expand depending on the loading direction. Since the individual Poisson ratio is different for fiber and matrix, the one direction in matrix and fiber will be non-zero. However, since no external loads are applied in one direction, the total force in one direction has to be 0. So this is another thing. So this is another condition that we need to apply. So for example, what I'm saying there is that you have a fiber which is surrounded by a matrix material, and I'm going to pull this guy. Now, this matrix has a certain Poisson ratio, nu m. This has a certain Poisson ratio, nu f. Now, as we pull it, the matrix might want to shrink like this. The fiber might want to shrink differently because its Poisson ratio is different. So what's going to happen, because now they are going to be, because matrix is constraining the fiber and the fiber is constraining the matrix, they will develop some forces in that one direction. Now what we need is to put a condition there saying that the total force in that direction has to be zero, because it is a traction free boundary. When we are applying load in the two direction, we are only applying here. There is no load being applied on this face or this face. So because of that, we have to ensure that that face is always unloaded. So we put another additional constraint saying integral of the stresses on that face has to be zero. And the other problem is the load transfer problem, which I mentioned, which is more apparent in finite element cases. So first thing what we will try to do is we'll try to implement this constraint condition. Okay. So, but before we do that, we will assume this problem to be a plane stress problem. Okay. And then by assuming plane stress, we have eliminated the third dimensionality of the problem. So all the three terms are gone. So we can write sigma 11 and sigma 22, which are the two stresses that are going to be present in this problem. And so we can write down the compliance matrix and the stiffness matrix for a two-dimensional plane stress model. And what we do is we substitute those expressions or the constitutive relations that I have shown into this integral sigma 1c dA. So the integral is again just repetition of the same constraint that I mentioned in the previous slide, saying that the lateral direction. So when you are, I'm sorry, the cursor point is sort of invisible to me, so I keep on. So this guy, as I'm pulling to in the two direction, what I am seeing is that in the one direction, I will develop some, fiber and matrix are going to shrink because of different Poisson ratios. So I am just explicitly enforcing a condition saying sigma dA along this one direction has to be zero. So by doing that, I'll get one constraint equation. We express the sigma 1c in terms of both the fiber and the matrix. And then from equilibrium, we know that the stresses in the two direction have to be the same in every layer. Using the constitutive relationship for the matrix and the fiber stresses and substituting that into the above equations, we will get a system of equations which can be solved for the epsilon value. And from there, we can develop a relationship for the fiber and the for the composite modulus. Okay. Now, there is a lot of algebra here. If you will have to go through every step as I've shown here. If you would do all the steps, you will get to the solution. Or there are, or you can use a symbolic software code like Maple or Mathematica, which can simplify your job. But ultimately, what I would like you to notice is that this algebra is arranged in such a manner that the equations are more or less similar to the previous derivation of E22 that we have done using simple strength of material based approach without the lateral constraint, the force equal to zero in the one direction constraint. There is an additional multiplying factor which is there, which is eta m and eta f, which are basically partitioning factors, which the derivation of those partitioning, the real expressions are given at the bottom of the slide. So essentially what it implies is that the traditional strength of material based formula of E2, you would have to use these eta f and eta m to improve the prediction capability. So this is one approach of E2 modulus calculation. Then similarly, another modulus that can be estimated using strength of materials is the shear modulus. Now, when we look at shear modulus of a composite, what does it relate? It relates the shearing stress to the shearing strain. Now, shearing strain is a change of the angle. So, which is what I am showing here in the picture to the bottom left, where this would be your gamma basically. So your delta is the displacement. Now RC is the radius of the composite. RF is the radius of the fiber, and so gamma will be delta by the height of this or the side length. So what I am going to do is I'm going to write down first the expression for shear strain in terms of delta by RC, and then same thing I can write for shear strain in the fiber and shear strain in the matrix. Now this delta also can be written as the combination of delta F and delta M. Now, from this expression, I can substitute the top expression for shear strain and write everything in terms of shear strain. So this is what I am doing here. So I'm using the above relations to substitute into delta equation, the displacement equation, and get the expression for the shear strains, and then use those expressions. Now we take this gamma value and we substitute that in terms of shear stress and the composite modulus, and gamma in the fiber will be tau by GF, and this will be tau by GM. And then what we can do is we can eliminate the common shear stress term, and we will get 1 over GC is equal to 1 over GF times VF plus 1 over GM times 1 minus VF. Again, this is same as the rule of mixture relationship that we obtained for E22 case. And again, in literature, what was found is that this simplified expression for GC was not correct. It was not giving a good match with the experimental data. And so similar work to the development of partitioning factors that I had shown in the E22 model was also done for the G12 case. And that was used, but then later on there is a set of researchers, Halpin Sai, one sec. So the equations that so these partitioning factors were found out experimentally. So they did a lot of experiments and tried to find the partitioning factors which can help in improving the prediction match. And what they found is that a partitioning factor of 0.6 seemed to work out quite well. Now, so in a sense, these are called semi-empirical equations because there is some physics to it in the derivation of the equation, but then we are using some type of a curve fit parameter to make this equation work better than the original equation. So it's a semi-empirical equation, but Halpin Sai is a very popular form of this equation, which people tend to use for shear modulus prediction. And so from strength of materials, what we have seen is we can estimate the properties of E11, which is the fiber direction modulus, then E22, which is the transverse to the fiber direction modulus, and then the shear modulus of the composite, G12 term. Now, the other term that could also be estimated with a strength of material approach is the nu12 term. And nu12 term is similar to basically you apply a stress along the one direction, which is the so this is one direction and this is two direction. Okay. Sorry for the inclined lines. Okay, this is better. This is 1 and this is 2. So when we pull along the 1, there will be a lateral contraction. Poisson ratio is nothing but the ratio of lateral strain to, so nu is, negative of lateral strain to longitudinal strain. So when we pull along 1, on the 2 direction, there will be a reduction in the dimension, and in the 1 direction, there will be extension. So in the 2 direction, delta 2 of the composite again can be written as delta 2F plus delta 2M. And we again use the same simplistic relationship between displacement and strain, as strain is multiplied by the thickness total thickness, and this will be fiber strain multiplied by thickness of fiber and matrix strain multiplied by thickness of matrix. And then we can also write epsilon 2 now. Epsilon 2 can be defined from the definition of Poisson ratio as nu1 2 times epsilon 1. And similarly, epsilon 2f can be multiplied again, expressed in terms of epsilon 1f as nu1 2f into epsilon 1f. Similarly, nu1 2m into epsilon 1m. And then we make the assumption that strain compatibility in the one direction. So epsilon 1f is equal to epsilon 1m is equal to epsilon 1, 1. Okay, so once you have that, you can eliminate all the epsilons, and you are then left with nu1 2 is equal to nu1 2f into vf plus nu1 2m into 1 minus vf, where vf is tf by t, okay, or tc. So tf by tc. Okay, so vf can be written as the tf by tc, and then we'll get a simple rule of mixtures for Poisson ratio. So this covers the strength of material based approach for estimating the moduli of the composite along one direction, two direction, the shear modulus in the 1-2, and the Poisson ratio. Now, the next approach is the elasticity based approach. Okay, in a elasticity based approach, the fiber and matrix are modeled explicitly, as I mentioned, and the interface conditions between them of displacement and stress continuity are enforced. So if you just compare with the previous strength of material approaches that I have talked about, we never really come to the actual interface of the fiber and the matrix. Our focus was always at a very high level. We never bothered what is happening to the load as it transfers from the fiber to the matrix or matrix to the fiber. There was no explicit conditions, mathematical conditions, which are enforcing some continuity of displacement or stress as we move from the fiber material to the matrix material. Now, in elasticity based solutions, we will explicitly account for that interaction. Therefore, it's obviously a lot more accurate, because in the previous case, as you noticed, when it came to the transverse fiber, if I'm looking at a fiber end, so for example, if this is my three-dimensional representation of a single fiber, what you would know, so if this is my two direction and this is my one direction, at the end, if I make a cross section and if I'm applying some load, I can clearly see that the load is going to have multiple pathways, as I mentioned previously also. It need not go only through the fiber. Now, in the previous strength of material cases, we really didn't account for that. The second approach of E22 was a little bit better in the sense that we sort of took into account the effect of Poisson ratio, the lateral contractions, and the internal forces that are arising because of the mismatch of Poisson ratio. But it was still implemented in a very integral fashion. So the whole surface on the one direction, we said, has to have zero force. Now, we didn't still account for the load paths that are going. So if I apply 1 Newton force on the top surface, it's not necessary that the fiber will see 1 MPa stress on the top surface. The fiber may not see 1 MPa because there could be load transfer happening through the matrix as well, and that can change the stress that is coming onto the fiber. But those were not accounted for, and that is why strength of materials has certain deficiencies. And so one thing you should remember is that strength of material based approaches are meant to give you 80% of the solution with 20% of the effort. So it does its job as a rough approximate approach to estimating the properties. Strength of materials approach does the job. But if you want accurate numbers, then strength of materials alone is not correct for all the cases. E11 is reasonably good. Rule of mixtures is actually pretty good compared, and it's comparable to the elasticity based solution or finite element. So rule of mixtures is a good way to estimate E11 direction properties of the composite. But when it comes to E22 or the shear modulus, strength of material based approaches are not that accurate unless you use the Halpinsa equations, which I showed previously, which had the partitioning factors. But then they are semi-empirical. So if your material system changes, or if you are using some new material, it is better that we test those materials ourselves and make sure that the properties are indeed following the similar constant values that we have used in the Halpin size standard equations. So these are some of the things that you should remember when you are estimating these properties. When to use strength of material approach, for what properties to use strength of material based approach, and also at what point you should maybe do a cross check. As long as you remember all of that, then you cannot really go wrong. Now let's come back to this elasticity based approach. So in the elasticity based approach, as I mentioned, the fiber and matrix are modeled explicitly. So what do I mean by explicit? That means we account for the geometry. So if it's a circular geometry, I'll account for the circular geometry. If it's an elliptical geometry, I'll have to account for the ellipse shape. Okay, and then the interface conditions. Interface is basically the point where you move from the fiber to the matrix. How is the fiber and the matrix bonded? Like, how are they bonded? Are they perfectly bonded? Do they have some disconnect between them? Or how is the stress transferring displacements? What are we enforcing displacements in terms of continuity wise? So these are things that we have to explicitly account for in the elasticity solution. So in a regular composite, thousands of fibers are present in random arrangement. Now again, once we talk about geometry and all of that, the arrangement of the fibers comes into picture. So the picture on the right tops of the screen, I have drawn a few circles indicating them to be fibers, and the blue is the matrix. Now you can see that the fibers are distributed in a rather irregular manner. Okay, there is no pattern to the distribution. The bottom one is more orderly and more nicely arranged. So the when we talk about fiber reinforced composites, the at low volume fractions, that means when the area of fiber is much smaller compared to the for composite volume or composite cross sectional area, what will happen? The fibers can be distributed in much more non-uniform manner. They can still be organized in a proper manner, but more likely that they will be distributed in a more irregular packing. But typically, as the volume fraction increases, the packing becomes more and more orderly, because there isn't that much space for the fibers to become irregular. I mean, when you're talking about 60-65%, pretty much all the space is taken up by the fibers. Now, the fibers will end up being having some type of regularity if you ignore the edges. So whenever you come to the edge of the part in the cross section, you might see irregular arrangements, but as you go to the core, you will see more regular arrangement or regular packing. So this packing is critical for elasticity based solutions. We have to assume a certain uniform packing, because we otherwise what's happening is that, see, when you have a uniform packing, we can assume that it's a homogeneously packed. Now once you have irregular packing, technically locally the properties are changing at every point, so homogeneity becomes less valid. But again, one thing you should remember, that the reason elasticity based solutions and all have survived is that typical composites that are used in structural materials, like when you're building a beam or a blade, or like a helicopter blade or a aircraft wing, the volume fractions are high, typically in the order of 60%, 65%, above 50, 50, 55, 60, around that. So since in high volume fractions, as I mentioned, the packing is not a issue, they are typically uniformly packed. These kind of assumptions all make sense and they work out. Okay, so at low volume fractions, it is an issue. But at low volume fractions, typically we don't use long continuous fiber composites. These low volume fraction composites are more likely to be chop strand or discontinuous fiber composite materials. And also the low volume fraction composites are normally not used as structural primary or a secondary load bearing structures, but they are more like tertiary load bearing, in the sense you might have a panel in the wall which is not really a load bearing panel, but it's just a you can say more like a barrier to sound or something, or maybe it's carrying a very light load. So those kind of structures you will see are used with these discontinuous and low volume fraction composites. So all in all, this packing assumption, or what we want is a uniform packing, does work out also with the practical usage of these materials. This is an exercise which I normally give to the students of my class. You can also try it out. Uh, it just requires you to write a small code, and as I'm mentioning here, you take a 1 millimeter square block and try to randomly arrange fibers of 6 micron diameter. 6 microns is the typical diameter of a carbon fiber, and you can try different volume fractions. I just given 10, 30, 60, but if you have a code, you can try different things, and you can see for yourself. If you pick a small 0.5 square millimeter square area in the center of the square, you can try to calculate the interfiber spacing, the mean interfiber spacing and the standard deviation for different volume fractions, and see for yourself how the packing becomes more and more uniform as the volume fraction increases. Um, I think it shouldn't take much time. If you have some time and interest, you can try this out. So next is, before we get into these elasticity-based solutions, there is also some terminology associated with micromechanics theory part. One is the representative volume element. Now, when I say representative volume element, is to consider a reasonable volume of the composite materials so that it is representative of the overall composite. So what do I mean by that? So as you see a picture on the right-hand side, what you see is that it's a small segment of a woven fabric. Now, typically what happens is that a woven fabric can be made by copying this piece. I can copy this, in all directions, and I can create a whole fabric. Now, when I'm trying to model this for micromechanics, if you recall back to the first slide when I said micromechanics is essentially we want to homogenize the properties. We want to get the effective properties of the composite. Then effective means I want to get properties which are representative of that material, isn't it? So in case of a woven fabric, suppose I only consider a small segment like this, and the one which is hashed in red. Then what happens is that segment representative of the smallest thing? It is not, because I cannot I cannot say that the properties I obtain from this will be the representative of the complete uh, composite. So for every structure, we have to try and find a arrangement of the fibers. Especially this is more common really for unidirectional composites. It's not an issue, because there is no geometry as such. It's just straight fibers, so it's not a big issue. But for woven fabrics or for 3D composites, identifying this smallest structure which is representative of the whole cell. So it is like it's like if I have this properties, if I can apply, so I will do all my modeling on this. I'll apply a unit loads along this. I can apply unit loads along the other direction. I can obtain the stress versus strain response, and the modulus I can obtain from there. Now, because if I just copy paste this guy, I can create a complete woven fabric. So therefore, this is a representative volume element. So we need to come up and identify those small segments which are representative of the big geometry, big architecture. At the same time, they are small enough so that we can solve it. So this is a important terminology. Especially this is more critical for finite element methods, really, where we want to identify this kind of representative volume element. The other terminology also which I want to share is the unit cell. This is many times used interchangeably with RVE, but I feel that unit cell implies a certain periodicity, and the concept of unit cell is more critical, again numerically modeling the fiber and matrix. it is expected that the edges of a unit cell remain straight after deformation. So imagine if you have if you have fibers which are running straight in this cylinder, then I would just I would take a unit cell which is like a fiber here and a fiber here, and so this is my, sorry for the wavy lines, but imagine them to be straight. Now this is the big composite. I could take just this one cylinder and do my analysis on that, and the properties that I get, I can say, can be estimated to be the properties of this big cylinder. So that is another concept of that is used. This is more common in finite element based micromechanics approaches. So then just wanted to give an idea about those terminologies. Although strictly speaking, for these for the kind of problems we are talking in this class, those terminologies don't really apply. As I said, it's more critical when you're doing complex fiber weave architectures. It's more critical. So let's come to the first approach and the most commonly used approach in the elasticity based micromechanics modeling theory is the composite cylinders assemblage model. Now, in that, this is as I'm mentioning here, almost it can predict 4 out of the 5 elastic properties using this approach. Um, one sec. So this theory was first, developed, or this approach was first presented by Hashin, Z. Hashin, and he has actually done quite a bit of work in the area of micromechanics of composites, and there are many papers attributed to Hashin in this area. Again, I'm sticking to actually micromechanics has different authors, but we'll just stick to this basic cylinder assemblage model. Then there is another author also which you might refer if you feel. The other is Christensen. There is actually a book on composite materials by Christensen, which also can be referred to. It has a very extensive treatment on micromechanics of spherical particles, continuous fibers, discontinuous, all the things. So if those who are interested in understanding or getting a deeper perspective of these micromechanics based approaches should can refer to this book by Christensen. And so Hashin and Christensen are some important contributors in this area, composite cylinder assemblage model. We'll then go to the basic assumptions of this model. So the assumptions are that the composite material of fiber and matrix is idealized to be infinitely long cylinders of fiber embedded in a matrix. So here the fiber and matrix are infinitely long. One of the advantages of these kind of assumptions is that we really don't care about the end boundary conditions. Okay, why do we make these kind of assumptions? Almost all these theories typically have some of these assumptions, which are always they are not just being done for the heck of it. They are being done because they simplify your mathematical problem. It allows you to eliminate some things and give a justification for it. And mind you, this is just a theory. So these are all assumptions. This is not reality. The theory can have whatever assumptions they want to make. They can, we can make any assumptions and build a theory. Ultimately, the theory's usefulness or the validity of the theory will be done with the experimental data. So only when the theory becomes, valid or validated with experimental data will the theory gain popularity. Now, the composite cylinder assemblage model is popular, and the fact that we are studying is because this model has stood the comparison or validation with experiments. People have been able to find that this model is pretty good in predicting the average properties of the composite, with respect to experimental data. So then the other assumption is fiber radius and the matrix radius is calculated based on the fiber volume fraction. The whole composite material space is considered to be filled up with these fiber matrix cylinders of varying sizes. So one point that I would like you to note down in the picture, as you can see, when you have two cylinders of equal size, if I bring them, there will always be an empty space. So what the assumption is that that empty space, we are going to fill it up with a tiny cylinder where the ratio of the fiber to composite is still maintained in the same way. So the volume fraction is being kept constant, but the cylinder itself could be shrinking in size. So we are considering that our composite is made up of these kind of infinitely long cylinders of fiber matrix, which are dependent on the volume fraction of the composite, and they are of varying sizes. Okay. Then next we come to the method. So longitudinal modulus. So only one example I'll take because I don't think we'll have time to go over more than that. Quickly, what I want to say, so what we do is you have seen the equilibrium equations in Cartesian coordinates typically. What I'm showing you here is the polar coordinate form of the equilibrium equations. We take a axisymmetric model of fiber and composite. Now, what do we mean by axisymmetry? Axisymmetry implies that theta dependency does not exist. So the beauty of axisymmetry is if a problem is axisymmetric, you are getting an exact solution with a two-dimensional problem. So in this case, what happens? All the theta direction equilibrium equations. So one second, sorry. So this second equilibrium equation can be completely eliminated because of axisymmetry. Anything to do with theta, we say is not required because there is no variation along theta. Okay, that is the assumption we are making here. Then also all the other terms, all the stress terms where there is a theta term involved, we can eliminate those terms also. So then we are left with only the radial and the z coordinate terms. So axisymmetry is no dependency on theta, ignoring, and so another thing, ignoring end regions in a very long fiber matrix, we can ignore the variation with z. So as I said, by assuming infinitely long, the derivative with respect to, one second. So we can, we can basically remove any term with dou by dou z. This can be, eliminated. These terms can be eliminated. Now, then we are left with only the radial equilibrium equation with only the sigma rr and the other term which is sigma rr and sigma theta theta. So we eliminate all the shear direction because we are assuming that fibers are too long and assuming axial loading and independence of response to the axial z direction. Therefore, shear is also eliminated. Now we are left with only the one radial equilibrium equation. So what we do is, so again, elasticity, just to give you a brief overview, there are three equations. One is equilibrium equation. Second is the compatibility or the continuity equation. And third would be the constitutive equation. So previously, just now, we saw that we simplified the equilibrium equations by axisymmetric assumption and by assuming that the z direction, there is no variation of properties. There is no z direction variation. And because of that, we are left only with the radial equilibrium equation. That's only one equation. Compatibility will be assumed by the continuity conditions. And the constitutive relations are what I'm showing in this slide. So I'm writing down the stress and the stress in the fiber and the matrix in terms of the material properties of the respective material properties and the strains, so which are shown in the top of the slide. And then because there are no shearing strains in this problem, the only normal strains are there. So epsilon z, epsilon theta, and epsilon r are given by this expression. Epsilon theta, if you recall from basic kinematics of strain, epsilon theta is dependent also on the radial displacement. Suppose, if you have a cylinder, you just imagine this cylinder expands. Okay, this cylinder expands to this. There is a radial displacement, but because of this radial displacement, there will also be a increase in the epsilon theta because there will be a increase in the circumference, which is now going to be strain. So epsilon theta is also not only dependent on v, which is the displacement along theta direction, but also dependent on w. So that epsilon theta is present. Then what we do is we take the radial equilibrium equation, we substitute these kinematic relations for strain in terms of the individual displacements, and convert this above equilibrium equation using the constitutive relationship to finally get a equation in terms of d2w only in terms of the radial displacement. I know the step from here to here involves a little bit of algebra. Either you can do it by hand or, as I said, so what you do, you substitute sigma rr in terms of strains using the constitutive relationship. So this equilibrium equation will be there for both fiber and the matrix. Okay, so I'm just telling you quickly. So sigma rr you substitute in terms of the material properties, and the strain, and then strain you substitute in terms of the displacement relationship. So finally, what you will get is this, because all the C11, C12, those terms will get cancelled out if you do the algebra correctly. Okay, and you should be left with a differential equation in radial displacement. The solution to this is given by the term in the box, the red box, which is AR plus B by R. And what we do is, now we have to look at the fiber and the matrix. So imagine this is RF, so, and this is RC. So what we'll do is, at R equal to RF, we will have some boundary conditions, and R equal to RC also will have conditions. Now at R equal to RF, radial displacement has to be continuous, because if radial displacement is not continuous, you would imply that there is some type of a D bond between them, which we are not. We are considering perfect interfaces where everything is bonded perfectly. So one condition will be the radial displacement continuity. Then the other is also that u has been considered to be independent of the radial coordinate. So again, we are considering axial displacement has no variation along the radius. So we can directly write axial displacement as the axial strain multiplied by the z, okay, or the axial length. And then the other one is that value of axial strain is constant, which is again from our assumptions that strain is same in fiber and matrix. Okay. Then we substitute this solution for the fiber and the matrix. And then one thing we find that for the fiber, if we go with the solution of the form that I'm showing here, at R equal to 0, this solution will tend to be infinite. It will blow up, isn't it? At R equal to 0, this will blow up. So to prevent that, the only way we can prevent that is if we put BF equal to 0. So by making that constant equal to 0, then the displacement of the fiber, the radial displacement of the fiber, will be a finite solution always. So AF into R, which means at R equal to 0, there is no radial displacement, and at R equal to RF, it will be AF into RF. Now at boundary condition R equal to RF, I mentioned earlier, we will enforce a displacement continuity, radial displacement continuity, and also stress continuity. Okay, so we will also say that the stress in the fiber and the matrix in the radial direction has to be the same. Now, with these two continuity equations, I mean the constraint equations at those interface, and using the constitutive relationship for the fiber and the matrix, we can solve the system of equations to obtain the three constants, AM, BM, and the AF. So these are the three constants that we have to find from our expression. So we use that. And once we have that, we can substitute them back into the respective expressions for the stress and strain to obtain the stress and strain relationships. Now, finally, so basically now what we have done, we have solved the boundary value problem. So we know now, given a fiber matrix system, we have the expressions for the stress and the strain in the fiber and the matrix domains. Okay. So now what is our task? We want to find E1C, isn't it? That was our main objective. So now what I do, I say that, okay, the total load that is acting on the composite. So total load that is acting on a composite is nothing but the integral over the matrix and the fiber. So I take the sigma F, I take sigma M, I integrate this over the matrix area, I integrate this over the fiber area, and I add them up. That should equal to the applied load T. So that equation I put down. And again, there's quite a bit of algebra there. But once you go through the algebra and you define the expressions for stress in composite as basically modulus times the strain in composite, and also say stress in composite, total stress in composite can be written as P divided by the total area pi RC square. You can get this expression for E1C, which is the Young's modulus of the composite. Now, this expression, if you compare to the strength of materials expression, is almost the same except for the term gamma and the delta. These are the expressions which are given at the bottom of the slide. So it's a lengthy expression, but so that is the difference between exact elasticity solution and the solution that you obtain for strength of materials for the E1C value. So you can always, I would request those of you who are watching this thing to try and solve these problems and actually compare for yourself between E1C and E1C obtained from strength of materials and that you obtain from this elasticity solution. That way you can see for yourself what kind of difference is there. But normally the rule of mixtures works out pretty accurate, I mean reasonable. There will be a small difference because of the exact solution, but E11 is not the one which has a major problem. Okay. So that's all. I will stop here for the micromechanics part of the lecture. It has, I think it might have been a little bit rush for some of you, but given the time constraints, and I thought at least I should give you a flavor of all the topics and maybe a little bit detail only on a few. So also I will be doing some of these lectures on Swayam Prabha DTH, which I do not know when the schedule is, but whenever it is, maybe you can follow it there. It will be in much more detail in that. Okay, thank you.
Thank you very much, sir, for the nice lecture. Now I'd like to ask some questions on the behalf of the participants to you. Hello.
Yes, please go ahead.
Yeah. One participant has asked the question, some composites elongation increases as the ultimate tensile strength increases. Why?
Sorry, your voice is breaking. Can you, I could not hear. You said elongation, ultimate strength, something, I
The
missed it.
participant has asked, some composites have elongation properties. It is increases with the ultimate tensile strength. Is that feasible? Hello?
No, can you just type it out, because somehow I'm just able to hear that elongation properties increases with ultimate tensile properties. Is that
Yes.
the question you said?
Yes, sir. He has asked that the composite having the illumination properties and that is increases with the ultimate tensile strength or not.
There is nothing like that. That elongation properties increases with ultimate tensile strength. I mean, if you look at carbon composites, for example, the failure strain is pretty low. Its tensile strength is very high. So I think it's a very material dependent property. I don't know whether there is any general thing like that.
And then another participant wants to know the field application of composite cylinder motor.
Sorry, 3 application of?
Field application of composite cylinder motor.
Sorry, I'm not able to hear your voice clearly.
He wants to know the practical applications of the composite cylinder motor.
Applications of composites.
Yes, practical applications.
Technical applications. Okay.
Yeah.
So, I mean, one of the biggest application of composites really are the wind turbine blades. If next time you I'm assuming many of your students are from Rajasthan, then if you go down to Jaisalmer and towards the Longewala side, or even towards Barmer side, there are so many wind turbines. Again, if you look at Gujarat side, there are so many wind turbines. All these wind turbines, the blades, which are the longest structures, actually one of the longest structures that are built, in structural engineering, I would say they are made with composites. They are 100% composite blades. These are you can't even imagine building them with metal. So composites, this is one big application. Now you look at Boeing 787 Dreamliner. It has also I think 60 to 70% composites. The wing is major part of the wing structure is made of composite. So these are just some of the few examples, but composites are yes, in the sense composites have mostly been used, are still being used in much more, I would say, uh, aerospace and defense sector than in regular civil structures. But slowly, when see, it's all a question of what is driving the design. If weight is a big factor driving the design, then composites become an automatic replacement. As long as weight is not a factor, people tend to continue to use the traditional materials.
So there is another question.
Yes.
For the homogenization, we prefer volume friction instead of the mass friction. Why?
With the homogenization equation,
Yeah, we prefer volume friction instead of the mass friction. Why? Participant wants to know.
so see, so this is again, actually what happened. There is a little bit of a difference here. When it comes to manufacturing on the shop floor, typically what you will find is people are using weight fractions. They will say we have used 30% weight fraction resin or whatever, you know. So it's all a question of convenience and what is the correct term. When I want to capture the geometry of a structure, I would be more interested with a volume fraction rather than a mass fraction. But when I'm manufacturing the composite, I don't really care what is the area fraction of fiber to the resin. I want to know how many kilograms of resin I want to use or how many kilograms of fiber I'm putting in. Therefore, in manufacturing, people convert it to weight fractions. In design and analysis, typically we use volume fraction because volume fraction enables me to make the geometry, capture the effect of geometry. Okay, because geometry is critical for us to estimate stress and strain. So that is why volume fraction is the natural term for design and analysis. Weight fraction is the term that is more commonly used in manufacturing side.
So there is one more question. It is possible to evaluate the damage evaluation properties
Is
using
it
the.
possible to
It is
is it
possible
possible
to
to
evaluate
estimate
the
the
damage
damage?
evaluation properties using
So damage
elasticity based approach. He has mentioned three approaches. One is the FEM approach, another is the strength of material approach, and third is the elasticity based approach. Which one is the better to evaluate the damage evaluation?
so just let me repeat the question. So is it
So I have
possible to
also mentioned
estimate the
on the
damage?
text chat box, the participant question I have mentioned
Yeah, so let me just repeat it. So is it possible to estimate the damaged properties of a composite using finite element, strength of material, or elasticity, or rather which one is better?
here.
Is that the question?
Yes, sir.
Okay, so yes, damage can be estimated. I mean, see, for in strength of material based approach, you can't do damage because see, to estimate damage, you have to uh, introduce a certain debond or a some type of a defect in the model. In strength of material, since really we are not considering it as a geometry at all, we are just simplifying everything into some springs. Now, estimating damage would be like, okay, you can always knock off the fiber modulus property by a certain fraction, but that wouldn't be very physically, correct. But in elasticity or a finite element based approach, damage has been done. In a elasticity based approach, for example, the E11 formulation that I created showed you can always introduce a interface crack or a debond between fiber and matrix over a certain region of the interface, and then you can solve the problem in the two domains, in the cracked domain and the uncracked domain, or in the debonded region versus the bonded region, and create certain continuity conditions at the crack tip. In the sense, you can say fiber is continuous, matrix is discontinuous. So based on that, so you can solve it. So there are many approaches to doing that. Yes.
So there is
Hello.
one more question.
Yes.
How to ensure that material is continuously distributed over the reinforcement.
How to ensure that?
Matrix material is continuously distributed over the reinforcement.
How to ensure that matrix material is continuously distributed over the whole reinforcement?
Yes.
Okay, so that would be a more of a manufacturing challenge rather than a mathematical challenge, because again, I just want to emphasize whatever I've shown today, they are all models. Okay, they are all theories, they are not reality. So we are just going to assume, because in theory we will always assume things are perfect, and that's how we will model things. Now we go to manufacturing shop floor and you go there, you will find that as actually volume fraction increases, dispersing resin into the fiber is not that simple a job. So there are different manufacturing processes. There is a vacuum resin transfer, there is autoclave based approaches where you apply some more positive pressure so that the resin can impregnate into the fiber architecture. So these are all things that can be done. There is no straight answer for that. It is a question of developing or adopting the right manufacturing process to make it, so that you can ensure the resin impregnation into the fiber to or fiber architecture.
There is a one more question.
Yes.
For the better mechanical properties, lay up angle of composite is required.
Sorry, would a better mechanical
Property.
property?
We construct the laminates using the lay-up angles at the 0 degree, 45 degree, 90 degree. So that is required at here.
I am sorry, I
So, okay,
could
I
not
am
hear your
writing the
voice.
question to the participant.
Yeah, can you please maybe write the question? Yeah. Should I stop sharing the screen? That way, maybe I can.
The question is participant asked, lay up angle of composite for better mechanical properties required. I have written the same question asked by the participant at here.
Okay.
Hello. Hello.
Is it possible to evaluate? Okay, no, okay. I'm just reading the question. Layup angle of composite for better mechanical properties. So that's a very, very broad question. I mean, if you're talking about unidirectional loads acting only in one direction, then you go with UD, just all the fibers aligned along the load direction. But if you have loads which are acting in multiple directions, then there isn't a single answer to it unless you have a you solve for it and you use the lamination theory, for example, which you must have learned, or maybe learning it in the later lectures. You have to use that lamination theory approach to to find out the optimum configuration of the layup so that you can calculate the best layup. So I cannot actually, nobody can give you an answer for that, because that's a very very generic question, broad question.
Sir, one request is from the participant side. They want the PPT of the expert lecture for their future
Sure.
reference.
Okay, I can mail it to you. I will mail it to you, and you can share with the students.
Sure, sir. Thank you, sir, for the wonderful lecture and
Thank you
the
very much.
questions to the
Thanks.
participants.
Yeah, thank you very much for organizing this. Thanks.
Thank you so much, sir. Your words have indeed given us the best picture on micromechanics and its fundamentals and has laid the foundation of this 5-day training program. Thanks a lot, and we are blessed to have you with us.
Thank you very much. I'll sign off then. Thanks.
Every sunset brings the promise of a new dawn, and hence we now approach to the end of this first day of this journey. Feeling thankful and not expressing it is like wrapping a present and not giving it. Now I take the opportunity to put all my gratitude into words. I, Urjasata Pridarshini Gaur, on behalf of the entire organizing committee of MBM Engineering College Jodhpur, sincerely thank and express my gratitude for all the eminent speakers for the morning, whose words of wisdom and knowledge have laid the foundation of this 5-day training program. I also express a sincere thanks to the audience for patience exhibited by them throughout this session. I also thank Imarti Ma'am, the coordinator of this training session, for giving us this opportunity to learn and explore new horizons and broaden our horizon as well. With this, we wrap up today's session and we will meet tomorrow, same time, for the next part of our journey on mechanics of composite materials and structures. With this, I sign off. Thank you very much. My pleasure, ma'am. Thank you so much.